So I'm Miles Lubin. I'm a PhD student in the Operations Research Center at MIT. Myself, Joey, and Ian are the developers of JUMP, and Madeline is one of the developers of convex.jl, and today we're going to present these two packages and how they fit together in the optimization ecosystem. So, sit down. Yep.
How it's like a volume down. On the top of it.
Yep.
Yeah.
So all of the notebooks are available on the JuliaCon 2015 repository under the JuliaOpt organization. If you want to check it out and follow along, we'll get to those in maybe 30 minutes.
Is this better? Oops. Okay, so it's pretty common for people to tell their backstory, how they got involved into Julia. So I'll tell mine. In 2012, I saw the original announcement. I just started hacking at it right away because I was coming from a background of scientific computing, C++, MPI, Python, Fortran, all of the above. And as soon as I saw the announcement, at the time I was working on implementing the simplex algorithm for a research project, and I said, let's just implement it in Julia and see what happens. So I made this, let's see, this repo in June 2012 for the implementation of simplex in Julia. I set it as a proof of concept of a large, complex application in Julia at like 800 lines of code. And I think at the time it was, but not anymore. But when I implemented it, I was able to get within a factor of 8, 10 of GLPK, which is one of the open source simplex implementations in C. And this is without doing a lot of the tricks and all the implementation tricks that go into a good implementation. I did a little bit, not too much. Under 1,000 lines of code, I could get within a factor of 10. That's pretty good for me. So then, fast forward to September, October of 2012. I was starting my PhD at MIT. I guess I walked over to Ian's desk and I said, let's write a modeling language, and we did. And that's how it started. So I'll let Madeline tell her story also.
Let's see. So I'm just going to hold it up. So I'm Madeline Udell. I'm a postdoc right now at Caltech. I'll be a professor at Cornell starting next year. In December of 2013, I was thinking about implementing some new optimization algorithms, and I was looking around at languages. And I wanted a language that had nice, easy access to linear algebra, and that would allow parallelism, because it seems like the sort of recent trend in computers is they're not, the processors aren't getting faster, but we're getting more of them. So parallelism is sort of essential to being able to speed up optimization algorithms long term. So I was looking around in Julia, and it had some very nice linear algebra, and I wanted to know how fast it was and how good the parallelism was. So I put together a package called parallel sparse matrix multiplication, because the core of many of the optimization routines I was interested in just involved multiplying by sparse matrices. And just implementing it in native Julia, I was able to get times that were competitive with MKL, which is Intel's sort of hand-tuned parallel sparse matrix multiplication library, among other things. And I thought, wow, well, this is pretty interesting. I think I might continue on in this language. And the main thing that I needed, a sort of core research tool that I use, is a convex optimization modeling language that allows me to express problems really easily and then feed them to solvers. That existed in MATLAB, did not exist in Julia, so I wrote it. Okay.
Okay, so what is optimization? It is not making code faster, at least when we talk about it. It is choosing from a collection of items and in some way choosing the best one. So basic idea is that you start out with a collection of items. You also have some way of deciding, comparing them, which one is better than others. And at the end of the day, we want to choose the best one. And so as optimization people, operations research, convex optimization, one way that we like to view optimization problems as in this form. So who's written down a problem like this at some point? Who's solved it on a computer? Okay. So just so that we're speaking the same language, we call these the decision variables. These define our collection of items here. F of x is some function of x. So x could be of a set of real numbers in a high dimension. F is a function from this high dimension into a scalar, and we want to choose an x such that the value of this f is minimized. And at the same time, we have some constraints that limit the options that we can take. So least squares regression. In this case, the decision variables are the coefficient vector x. The objective function is to minimize the squared distance of the prediction ax from observations b. Constraints, in this case, we have none. But if you want to add a constraint, then you get non-negative least squares regression, and all we've done is add the constraint that these coefficients are greater than or equal to 0. So I guess from our perspective, they're specialized algorithms for least squares, but as soon as you start tweaking the objective function, start tweaking the constraints, then we no longer use these very specialized algorithms. You don't have closed form solutions. Instead, we kind of try to bring them into a general framework of optimization, convex optimization. So these two fall into the class of model fitting, least squares you can add some regularization to change the objective, logistic regression, different objective, support vector machines, slightly different formulation, matrix completion, neural networks. We view these all as optimization problems. Some are easy, some are hard, some are convex, some are not, but they're all optimization problems. Another kind of different type of optimization problem is more of a decision problem. So here, these are kind of abstract coefficients in a regression, and they have some interpretation, but they're not always immediately interpretable. They're just coefficients to fit a model. In decision problems, usually your decisions are, for example, choose some edges in the graph such that we connect a start node to an end node, and the length of a path is minimized. So this is a shortest path problem, and our decision variables are the set of edges. The objective might be to minimize the length of a path, and our constraints are actually that the edges that we choose must form a path. And again, there are specialized algorithms for this. You learn them in intro computer science. You can solve these problems very efficiently, but what happens if you want to add a bit more? So for example, let's say the path can only have k edges, or you must visit at least one blue node when you go from the start to finish. What do you do then? You can't really do Dijkstra. You have to move it into a more general framework of the kind that we can try to address in optimization. Oops. So some similar routing planning problems: shortest path, maximizing flow through a network. That's packet routing. It could be trying to compute an optimal power flow over an electric grid. It could be the traveling salesman problem for vehicle routing. You might be FedEx. You might want to schedule deliveries. These are all the kinds of field of problems that if your problem feels like this, then come talk to us. So just a bit more. If you're allocating resources, you might want to decide which items to buy at an auction. You want to maximize the value, but you have a certain budget. This is a very classical diet problem, which was actually one of the first motivations for linear programming in World War II, where you want to decide, for example, how much food to buy, minimizing costs while providing sufficient nutrients and calories. Scheduling, how do you schedule nurses in a hospital? This is a problem that people use these tools for every day in practice. Optimal control, if we are designing a rocket, which we'll do today, we might want to decide the sequence of thrusts when launching a rocket so that at the end the rocket can achieve a maximum height subject to fuel capacity and the laws of physics. So these are the kinds of fields of optimization problems that we can solve in our framework, or attempt to solve. So I'll hand it over to Joey.
Is this good? Can people hear me? More? Okay, I guess I'll hold it up here. Okay, so why is the kind of the mathematical part of this necessary? So we've kind of presented these kind of classes of optimization problems, but you can think of like the network problem Miles was talking about. There's no kind of reason we necessarily have to express that in a mathematical language. So what's going on here is kind of without extra knowledge of the structure of our problem, we really can't do anything better than just taking all the items in our collection, feeding them through our scoring function, and just picking the best one. Right? So mathematics kind of gives us a natural framework for kind of encoding this structure in a way that we can understand and that we can actually kind of construct algorithms around. So at the end of the day, what we want is kind of a mathematical description of the decision variables, the sets of constraints, and our objective function. So what do these what does the mathematical description of these types of problems typically look like? So kind of the most basic types of constraints or objectives you can run into are just linear equalities or inequalities, right? So you have some linear affine function of your decision variables. It's kind of the most simple that you can get. Kind of the next generalization of that might be some kind of polynomial, so some kind of polynomial on your decision variables. The next is kind of maybe a little bit more opaque first looking at it, but some notion of set inclusion. And typically, kind of in the purview of this workshop, we're going to be working mostly with cone inclusion, so especially Madeline's talk. So the idea here is that you have some constraint or variables, and you want to impose that variable or constraint lies within some set or some cone. So you can think of ax minus b, so that'll give you a vector of expressions, and you want that to lie in the non-negative reals. Or something like x, which is an n by n matrix of variables, and you want that to be a semi-definite matrix, which is also a cone. We're going to be working a lot with some kind of integrality conditions. So we have some decision variable x, and we want to say that it can only take values 0 or 1. So this is a really powerful kind of methodology for modeling discrete decisions, but it also can make problems much harder to solve. So there's kind of a trade-off sometimes. And we're also going to be looking a little bit at some kind of logical conditions, or at least from a modeling perspective. Right? So a lot of the times you'll want to just impose some logical conditions in your decision variables and just verify that it holds true at any solution that you produce. Okay, so just really kind of quickly, I want to provide a taxonomy of some kind of optimization problems that we're going to be working with. So this is by no means exhaustive, but this is some kind of the vocabulary that we're going to be working with for the rest of the workshop. So it's kind of important that we're all on the same page. So we're going to say a linear optimization problem is just kind of the most generic or simple one that we're going to be working with. It's just where everything is a linear function. So all the constraints, all the objective, everything is just nice and linear. And quadratic optimization problem is going to be, now we're going to generalize that, and it's going to be maybe have some quadratic objective function or some quadratic show up in the constraints. So this is a generalization of linear. Kind of next is a conic optimization problem. So here we're going to just impose that the variables or cones kind of lie in some, variable constraints lie in some cones that we're going to define. And so you can kind of express linear and most quadratic programs kind of in this framework. And so Madeline's going to be talking a lot about naturally convex optimization. So this is just kind of the setting where all the constraints and the objectives are convex functions. And kind of beyond convex optimization, we have integer optimization, right, where we have some integrality conditions on the variables. And kind of finally, we're going to use nonlinear optimization. It's kind of a catch-all for everything else that doesn't fall into this kind of the framework that we have up here. So just kind of think of, just generic algebraic functions of, sines, cosines, exponentials, things like that. So the solvers that we have exposed kind of through the JuliaOpt stack, this is kind of some of them in the different problem classes that they support. They kind of fall into two main categories. So we have open source solvers that you can just download and use for free. And then there's also these commercial solvers that companies kind of produce, and they invest a lot of time and effort to make them work really well for a lot of instances. And many of them have fairly permissive academic licenses if you want to use them for research purposes. But if you want to use them in an industry setting, you have to buy a license, which can sometimes be pretty pricey. So the open source linear solvers are CLP and GLPK. Groby and Cplex are kind of the best of breed commercial solvers. Groby and Mosic are commercial quadratic or second order cone solvers. Ecos is an open source alternative. In the kind of conic setting, we have SCS, which I think Madeline's going to use later, and Mosic is a commercial option. Groby, Cplex, Mosic, CBC is the open source integer programming solver that's kind of available. And kind of for the nonlinear setting, we have IPOpt is a really good open source option. And also NLOpt is slightly different in kind of its focus, but it's also available through the JuliaOpt stack for these kind of nonlinear problems. And that's by Stephen Johnson. So kind of, this is kind of a really, really rough sketch of kind of what are the limitations of these different problem classes that we've laid out. So this is certainly not gospel, but kind of, I want to impart the idea that you can often solve really large scale instances, much larger than you maybe would think. So kind of in the linear setting where everything is really nice and simple, you can fairly routinely solve problems that have millions of variables or constraints. You can solve really large scale instances a lot of the time. In these kind of quadratic problems, you can also solve pretty large instances, maybe like an order of magnitude smaller, but the solvers are still quite capable. And in the conic setting, they're also quite good, but maybe another drop down the ladder. And so kind of beyond that, there's much more kind of variability you run into. So these integer programming solvers are really, really effective for lots of problem classes, and they can solve really large instances, but you can also kind of cook up pathological problems that can kind of break them that are relatively small. And this is maybe even more so true for the nonlinear solvers, where you can come up with problems that have like tens of variables that just kill the nonlinear solver. So again, these numbers are not not meant to be taken seriously so much, but I just want to impart the idea that just because you write down a problem and you look at it and you realize you have a lot of variables and constraints does not mean that you can not solve it. Just give it a try and maybe you'll be surprised. So what is the kind of the typical kind of process you go through when you have an optimization problem? So kind of from conception to actually when you sit at your computer and you look at it and you get a solution back. So typically you'll start down, you write some nice mathematical description of your problem, you'll kind of have some abstract representation of it. And then you'll go and look and say, all right, I look at these objectives and these constraints, and I can identify some structure to them. So I have these sets of constraints that are linear. Maybe these are quadratic or whatever. And then you can look at maybe some other structure that you have, but doesn't quite fit into this framework that we've laid out. So things like norms or absolute values. You can look at those and say, all right, they're not immediately representable, but I can perform some transformations, kind of maybe add variables or constraints and get it into a form that I can actually pass off to the solver, and it knows what to do with it. Right? And so once you have done these transformations and turned it into a class of problems that a solver is going to know what to do with, you can identify kind of an algorithm in a piece of software that you can actually use to produce a solution. Right? And so that algorithm, or that solver, that piece of software, is going to want the data in a particular format. Right? So maybe it wants a bunch of sparse matrices, or it wants to be able to evaluate the derivative of particular functions at given points. So kind of depending on the algorithm and how it works internally, it's going to want the data in a different way. So you recognize that, and then you take your math up here after these transformations, and you kind of massage it into the form that the solver actually wants to work with. And then you can just code it up, and you pass it along, and you get your solution, hopefully. Right, so this is kind of a silly little schematic of how this might look in Julia. So think of, you have some type that represents an optimization problem, and you have some type parameter t that kind of classifies it based on what kind of, where it falls in our kind of taxonomy of optimization problems. And then you just have this blob of data here that kind of represents an abstract representation of your problem. Right, and so you can think of it, it's just you're using multiple dispatch in a way. Right, so you have this classification of the type of problem that you're working with, maybe a linear or semi-definite optimization problem. You have integer, maybe it's kind of a least squares type thing. And then based on kind of the type of problem, you specialize and pick a different solution method. And so you pass in the data, and so for a linear problem, you might want to use the simplex method, or a branch and bound for an integer program, right? But that's kind of at a very high level, and so there's obviously some details we need to get into, right? So kind of naturally, the first question might be, how do we actually recognize the problem class that we're working with? How do we know that this blob of data represents something that is a linear optimization problem, or it's an integer optimization problem, or whatever? And then once we have kind of classified in this way, how do we actually translate our blob of data into something that's actually useful for the solver, right? But even before that, how do we get our blob of data programmatically into our computer, right? So we have our math before. We have some kind of expression of the problem in mathematical terms. But how do we actually kind of build that up in terms of something that Julia and the computer is going to be able to understand? So essentially, jump and convex are tools to help you build this blob of data, kind of in memory, a representation of your problem. And then what it's going to do is it's going to do 1 and 2. It's going to classify your problem and then massage this blob into something that's useful behind the scenes. Right, so jump and convex are what are called algebraic modeling languages. And essentially what they do is they help you turn this, so this big mess of math, into something like this. So this is something Julia understands and is able to pass off to a quadratic programming solver. This is typically the form they're going to want it in. So they're going to want a sparse matrix and a vector to encode the objective function, a sparse matrix, and lower and upper bounds, vectors of floats to represent kind of the linear constraints, and then some variable bounds, right? So just a big mess of data that we get from this, right? And so for a lot of these problems, there can be a lot of really nice structure, but also, you can get pretty large scale and kind of, I don't know, this is one particularly kind of pretty, this is the sparsity pattern for a constraint matrix of I think it's a linear program. But yeah, you can imagine that you wouldn't actually maybe want to build this up by hand, write a bunch of for loops and actually construct the sparse matrix yourself programmatically. So essentially what the algebraic modeling language does is it kind of automates a process that is tedious and error prone. So actually sitting down and writing a C or C++ code to actually construct these sparse matrices, they can get hundreds of thousands of lines of code. And you can think that if you're writing that much code, it's pretty easy to get something wrong. to misplace an index or, miss a negative sign or something like that, and then all bets are off. Also, that process is pretty opaque, right? If you have 1,000 lines of C, you can't immediately look at it and pull out the mathematical structure that you had to begin with, right? So you can think of it, you started with math, which is really pretty, and you can pass it to somebody else and they understand what you're working with. But that process is not invertible when you're working with kind of directly with the problem representation. You can't look at a 1,000-line C program and immediately pick out the math backwards. And it's also not portable, right? So if you're working directly with the problem representation, different algorithms want things in pretty different ways, right? So if you decide you want to kind of append new constraints to your problem and change the problem type or change the solver that you're working with, oftentimes you're going to have to rip a lot of the code out and start from scratch. Okay, so the goal of an AML essentially is to provide a direct translation of the math that you write at the beginning to something that works as kind of valid code, to build things up in memory, pass it off to the solver, and get your solution back. Right? And so jump and convex are kind of two tools that, two AMLs that kind of fall under this category, but they're kind of complementary. They both serve the same function, but they kind of emphasize different things. So jump is focus on large scale or larger scale instances with kind of complex indexing or logic involved. And it kind of exposes these advanced solver features. So it's really meant for large, complex problems. And some of these instances, you can run into situations with other tools like this where you actually spend much more time building up your abstract representation of the problem before you even pass it off to the solver. And you can run out of memory, and you run in these situations where the tool that you're using to make your life easier actually makes it so you can't actually solve your problem. On the other hand, convex is really focused on this reformulation step that I mentioned, right? So you have some mathematical description of your problem, and you need to do some massaging and kind of translations to actually turn into something that you can then pass off to the solver. And often there can be like kind of multiple steps you have to go through to do these transformations, and it's often not clear at all how you actually do that. So convex is really here for doing that automatically for you. And they kind of use this grammar of convex optimization to actually kind of do these transformations in a way that they can ensure that the problem is going to remain convex, which is a really important kind of property for a lot of these solvers and kind of from a theoretical perspective. So at the end of it, you get an automatic proof of convexity, which is nice. So why Julia? Why did we decide to kind of build these tools in Julia where there are other tools that kind of do these things at the same time in other languages? Essentially, it's because of all this. So there are other tools out there that kind of maybe can capture a couple of these at a time, but not really, kind of more than half maybe. So the C interface is really, really important for us because these solvers typically provide shared libraries that you can tap into, and especially for larger problems, you really don't want to be kind of going through the file system, writing something to disk to represent your problem, pass it off to the solver. You really want to be working in memory. Also, macros and metaprogramming, especially for jump, we can kind of take advantage of that to let you write like DSL-like code, and then kind of do some transformations to produce ugly, more efficient code at compile time, to kind of avoid things like copying that are kind of implicit in the operator overloading that we have to do. We also use multiple dispatch. We have an interface layer between the solvers and the modeling language that kind of jump and convex kind of both talk through. And so multiple dispatch provides kind of a nice, clean way of kind of implementing this interface. So performance is also a big kind of advantage of Julia, but it's also really important to have it in a real, kind of having these modeling tools in a real programming language for doing things like data wrangling or post-processing your results. So there are commercial tools out there that are kind of standalone C libraries that kind of have their own modeling language you can work with, but as soon as you want to kind of do something outside of their kind of provided list of functionality, you're really screwed. So if you want to do things like compute an eigenvalue of a matrix or do a for loop but do it in a slightly different way than they allow, there's not really much you can do because it's not a real programming language. Also, composability is really important for us. You can do things like write advanced algorithms that solve optimization problems kind of as subroutines or solve optimization problems inside optimization problems. So you can do some cool stuff there, and it's just a fun language to work with, as I'm sure all you guys know. So, Madeline.
I'm going to try attaching this and see. Tell me if you can't hear me, and I'll try some other system. Okay, Jahao says it's good, so I'm going to hope it's good. Okay, so in order so that you can follow along, I would like. So does anyone not have Julia installed? We heard it was possible. We heard it was possible. If you don't, you can raise your hand and one of us will come over to help you. But if you do have Julia installed, then there are just two things you need to do. You need to first install convex. So, whoa. And please use Julia 0.3 if possible. No guarantees about things working on 0.4. Some solvers work, some solvers don't work. We don't control all the solver developers. So what I'm going to be saying is targeted at 0.3. Okay, so add convex. And also we're going to be using the solver SCS. And then go ahead and clone that Git repository, and you'll be ready to go.
And kind of throughout, if you have any questions or run into problems, just raise your hand, and one of us that is not speaking will come up to you and kind of help out.
Great. And is the font large enough? This is always the... Good? OK, great. So first of all, I want to give a shout out to the rest of the convex.jl team. This has been a group endeavor. I sort of started the project early in 2014. And Karanvir, David Zhang, and Jenny Hong were taking a class at Stanford, and they said, yes, we want to help, we want to make this real. So they got a couple of backends working and sort of refactored the code, made it much nicer. So it sort of turned it into a really robust system. We've also have to thank CVX, which was sort of the original modeling language that really used this paradigm, and CVX Pi, which is another version in Python of a similar idea. OK, so the first thing that I want to motivate is why are we interested in convex optimization at all? Why should you be using a package called convex? And the real reason is that convex problems are the only ones that we can guarantee that we can solve efficiently. So let me try to give some understanding for why that should be. So first of all, let's think about, we talked about this idea that you start out with some set in which your decision variable might lie. And your life is going to be a lot easier if you had some decision variable that you liked, that had some value that was pretty good, and you had some other value of the decision variable that had an OK value of the objective function. It was like pretty good. And you might say, well, that one's pretty good and that one's pretty good. What about all the ones in between? And if your problem is convex, then all of those are also feasible. They also lie in your set. They're like valid decisions. And every single one of them is going to be at least as good as the two endpoints. And so that's a property that's very pleasant for solvers. And it turns out that if you have this property, then solvers can go about sort of going downhill and always knowing that as long as they keep going downhill or they keep doing reasonable things, they're going to get to the global optimum. And in fact, right, once if you're somewhere, right, and then you look around yourself, and you see that all the points immediately around you are have higher values, they're less good than you, then you know you're at the global optimum. There can't be anywhere else that's as good as where you are. So it's easy to find optimal points, and it's easy to certify that you're optimal once you're there. We're going to need to learn how to recognize convex optimization problems so we can make sure that we're actually solving the optimization problem that we think that we are. I'm going to be using some of these words throughout this talk. A convex combination of points is just any point that lies on the line between them. A set is convex if every convex combination of points in the set is also inside the set. And a function is convex if it always lies, if it looks kind of like this, okay? So every line connecting 2 points on the graph of the function always lies at least not below the function itself. And we're mostly, so this idea that convex combinations of points always have better values is just exactly described by this property. If this point was feasible and that point was feasible, and then we took any point in between them, right? So any point in between those two x's, we get something along here, and that's always below the convex combination of their values. So when we take an average of 2 points that are feasible, we always get a point that's no worse. And by saying no worse, we're implying that we like to minimize functions. Maximization is fine too. You can just sort of imagine everything flipped by a negative sign. If you wanted to maximize, you can minimize a convex function, or you can maximize a concave function. And this package will sort of do that transformation for you, so you don't have to worry about that kind of thing. So the traditional form for nonlinear convex optimization problems looks something like this. You say, suppose I want to minimize some objective f0 of x. That tells me how annoyed I am to have decided on these values for these variables x. And the only x's that I'm allowed to pick are the ones that satisfy fi of x is less than or equal to 0 for every I, and hi of x is equal to 0. And in order for that problem to be convex, I need all of those fi's to be convex functions, because that means that those constraints, the sublevel set of a convex function, every point that has a value of that function that's less than or equal to something is always a convex set. For quality constraints, I actually need those functions to be linear. Okay, so if you want to think about this in a more intuitive way, you can say a problem is convex if every convex combination of feasible points is still feasible and has an objective that's no worse, has an objective that's colloquially, we might say, better. Okay. So there's something that's a little bit hard for solvers, that can be a little bit hard for solvers about this nonlinear form, which is that suppose I'm at a point x, right? You have to think, if you're a solver, right, you need to know, what do you know about these functions, right? Where you're going to move from this point x is going to depend on what you know about that function f0 and what you know about those functions fi and that function hi, right? So oftentimes the paradigm, and the one that you're going to hear about later using jump, is this paradigm that what I know is, I know which direction is downhill. I know derivatives. Okay, so here I am at a point. I can move downhill, so I like step over here. Okay, here I am. I check which direction is downhill. It's over there. I step over here. Okay, so you can imagine this might take, it might take a long time, right? You don't have sort of a global knowledge of what's going on. Also, how do you even know those functions are convex? How do you know that if you just keep going downhill, you're going to get to the global optimum? So you might know that because you have other knowledge about the problem, because you can look at the whole thing, but the solver is going to be going stepwise and can't really tell. To make life easier for the solvers, one sort of big trend over the last 15 or 20 years has been to move to a different form for optimization problems, which is to say that they're in a conic form. And here, we're really telling the solver everything it needs to know about the structure of the problem all at once. In a sort of in a small number of bits, we can communicate to the solver everything it needs to know about the structure of the problem. And the structure is as follows. We're going to minimize a linear function, C transpose x, subject to linear constraints, and the additional constraint that x is in a cone. And here's what I mean by cone. I mean that if I've got a bunch of points that are if I've got a bunch of points in the cone, then I know, and let's say this is 0. 0 is right over here. Then if I multiply any positive number by one of these points, I get a point that's still in the cone. So that means this entire line is in the cone, that entire line is in the cone, that entire line is in the cone, that entire line is in the cone. And if it's a convex cone, then it means every convex combination of these points is also in the cone. So it looks kind of like that. And there are certain standard cones that these optimization solvers know how to deal with. They know what their structure is, and they know so they can sort of optimize them more easily. And the canonical cones are things like the positive orthant, the set of vectors, all of whose entries are greater than or equal to 0. The second order cone, those whose two norms are less than or equal to something that's affine. This is also sometimes known as the ice cream cone, sort of smooth around the sides and goes up. And the positive semi-definite cone, which I won't talk much about here, but it's the set of symmetric matrices, all of whose eigenvalues are non-negative. And so there are a lot of nice functions that you could express in that way, like operator norm, nuclear norm, maximum eigenvalue, minimum eigenvalue, things like that. We won't talk about that here, but if you have problems like this, let me know. OK, so why are we doing convex optimization? I've already said a little bit about it. It has a beautiful theory with a sort of you can prove optimality. You can use duality in order to figure out sort of how much a certain constraint is affecting your solution. You can get the global solution. You can prove it. You can do that provably quickly. It conceptually unifies a number of other methods. And it's also useful for non-convex problems. So understanding what's going on here will help you when you get to problems that are harder. Basically, all solvers use convex optimization as a subroutine. And then there are tons of applications. And we're going to talk about a couple of them here. Mostly, we'll be talking about data fitting problems, where control style problems are going to be in the jump presentation later. OK, so convex.jl, what's the idea of it? You get to write your problems in a form that looks kind of like the first form that I showed, where I get to use sort of function composition. And it's going to translate your problem into conic form so the solvers can solve it quickly. So here's an example just so you get the idea. I'm going to be using the convex package and the SCS solver. I'm going to generate random problem data. A and B, so A is a matrix, B is a vector. I'm going to create a variable that has length n. So an n-dimensional variable. It's my decision variable. And here's what I'm going to do. I'm going to write my problem is just to minimize the sum of squares. Oh, sorry, that's from a future version of convex is taking out underscores. Right now, it still has underscores. OK. OK, I hear different views about the utility of underscores. Anyway, so we're going to minimize the sum of squares of ax minus b, subject to x being greater than or equal to 0. Okay, and this looks like the math. It's very easy to see what this is doing. It doesn't look like conic form. When I solve the problem by calling solve exclamation mark, it's going to convert that problem to conic form, and then call the SCS solver to solve it. And it'll tell me the problem value. OK, so it solved it to optimality. And it tells me the optimal value is 0. And that's not too surprising, given that I have fewer constraints than I have variables, though it's a little bit surprising because I've got all these positivity constraints. And in fact, if I solved it again, I might get an optimal value that was non-zero, because the positivity constraints are keeping me from finding anything that exactly satisfies ax minus b is equal to 0. OK, so I just want to quickly go through what are the kinds of things that you can do with convex. So first of all, you can create a scalar variable just by calling variable with no arguments. You can create a vector variable by calling a variable with an argument that's the length of the vector you want to create. A matrix variable, one that's a 4x2 matrix. It's created like this. Convex thinks of everything as being a two-dimensional matrix. So it's sort of going to convert things to two-dimensional matrices behind the scenes. It just makes sort of our understanding of linear algebra a little bit easier. But that shouldn't be something that sort of the user has to worry about. And by the way, if you have questions anytime along this, right, this is supposed to be a tutorial, like, please ask them. Don't hold back. OK, so expressions. you can use a large number of functions on variables to form new expressions. The real restriction is that we need to be able to know behind the scenes how to turn your function into a conic form. So we have a lot of, I'm going to exit this for a moment, if I can. Ooh, nice, OK. So we have a lot of functions that are supported. A lot of the sort of standard functions that you would just be using if you were expressing mathematics in Julia. Yahao has a question, maybe?
Sorry to interrupt. The people here who are having trouble connecting to Git for package add.
Oh.
This was a network problem.
They don't need to be on. They need to leave MIT guest and join MIT. Which was the Wi-Fi network.
Also, EduROM is not good either. MIT is better.
Yeah. What needs to be done to connect to GitHub?
You need to leave the Wi-Fi network MIT guest and join the MIT Wi-Fi network.
MIT Wi-Fi, that's its name.
Just MIT.
Just MIT. Okay. Thank you.
OK. OK, so on the convex.jl docs, you can see a lot of the atoms that we have. So things like, normal, multiplication, subtraction, division, things like diagonals of matrices. The sum of the largest elements is sum of the smallest elements. You can reshape things, take minimums and maximums, absolute values, negatives. OK, and then there are lots of other sort of atoms that are a little bit more complex. And all of these, we need to know how to convert them into our standard conic form. Log, exponential, entropy, even like log determinant, which you might have seen in Ian's presentation yesterday. OK. But what's nice is that you don't need to know how to convert these to conic form. All you need to do is to be able to type things like x plus 2x, or x plus the first element of y. And convex.jl is telling you that it knows that this is an expression, that it doesn't know the sign of it, because you haven't told it whether these variables are positive or negative, but it does know that this expression is affine, which means it's both convex and concave. On the other hand, if I were to type maximum of y, then it knows that this is something that's convex, because it knows about the maximum, and it's taking the maximum of this of just an affine expression, and it knows that that's a convex function. Similarly, I could take the minimum. It would know that that was concave. And if I tried the minimum of the if I tried the maximum of the absolute value, it's totally fine with that, because it knows that if it composes maximum with absolute value, that's still a convex function. And we're going to say more about how it knows that later. But if I try to compose minimum with absolute value, then it gives me this warning. It says the expression is not DCP compliant. Trying to solve non-DCP compliant problems can lead to unexpected behavior. What it means by that, it doesn't know how to prove this is a convex problem. And as long as it doesn't know how to prove it's a convex problem, it might not solve the problem you think it's solving. Okay? So this warning should be taken very seriously. If you really know what you're doing, then go ahead and do something with what it returns. But this is not, it is not guaranteed to solve your problem if you see this. Yes?
What is DCP?
DCP is disciplined convex programming. And I'm going to talk more about that later. Right, so it doesn't know how to prove it. You might give it a problem that is convex, but it can't prove it's convex. It can only prove things that are convex if they obey a certain rule set called DCP. But if it can't prove it's convex, then the transformations it's using to solve your problem, give it to the conic solvers, might not be valid. So you should probably use a different package for your problem, or figure out how to re-express it in a way that is DCP. And sometimes that re-expression will even make your problem faster to solve. Any other questions? OK. Constraints. OK, so we can make any constraint as long as it's convex. OK, so a constraint is convex as long as a convex combination of a feasible point is also feasible. Every feasible set has to be a convex set. So in other words, right, so if our function is convex, then the set of points that are less than or equal to some value is always a convex set. If our function is concave, the set of points that are greater than or equal to some value is always a convex set. So we're fine. And if our function is affine, then we can not only ask for it to be greater than or equal to something or less than or equal to something, we can even ask for it to be equal to something. And that's going to be a convex set still. OK, So our constraints have to be convex less than or equal to 0, concave greater than or equal to 0, or affine is equal to 0. Okay, and affine is a special case of both convex and concave. Okay, so let's try it out. We can ask for x to be less than or equal to 0. Okay, and it can tell us this is a perfectly good less than or equal to constraint. The left-hand side is affine, and the right-hand side is also affine. What about this one? X squared is less than or equal to 0. X squared is a convex function. So this gives us a nice convex constraint. Then how about x squared is less than or equal to the sum of y?
Can I just ask a question?
Yeah, please.
I see it says the right-hand side has convex convexity on the second example. It's 0. In the first example, it's affine convexity. What changed about the right-hand side?
You know, I'm not sure. That's an excellent question. So in 45, it knows the sign because it knows that squared, the range of squared is the range between 1 and infinity. Between 0 and infinity. So it knows it's always positive or non-negative. Whereas x could be anything. X could be -2. X could be -1,000. So it doesn't know that x is going to be positive. Doesn't know the sign of x.
Is anyone having trouble getting the notebook loaded up and running?
Should be able to do it on JuliaOpt as well.
Oh, yeah, that's true.
CNQ didn't load 310.
Okay, if there's any, raise your hand and I'll walk by.
Yeah, because I think installation problems are one by one. But we have 3 people who can help. So raise your hand high if you want someone to help you install. Good. Thanks. Okay. X squared is less than or equal to the sum of y. Thoughts on whether so is this convex, and if so, why? Hiding the output.
The part that's putting out positive and no sign, is that coming from your code?
What was that?
Where it says positive?
Yeah. So this is what my code is able to infer about these expressions.
Change it to non-negative.
Hmm?
Change it to non-negative.
Sure. Mostly because it's shorter. Yeah.
It's kind of grating.
It,
OCD.
sure.
The
Yeah.
notebooks are only compatible with the new version of Jupyter.
Okay. So what should we do about this? So, okay. The notebooks are only compatible with the newest version of Jupyter.
Yeah.
So not with older versions of IPython. Or?
2.4 can read them, but not previous versions of IPython.
I see. Versions. So IPython 2.4 and above can read the notebooks.
Okay, so who's having trouble opening the notebooks? A few.
So JuliaBox might be a good option rather than trying to install things yourself.
I can install things, but just tell me what to
Okay.
install.
So install Jupyter.
Yeah, update IPython.
Update IPython. Yeah.
But, I mean, you might want to just
The newest version.
walk people through getting notebooks on JuliaBox.
Okay. Actually, do you want to? I haven't done much with JuliaBox. Do you want to?
Okay.
It's probably worthwhile.
Okay.
Right.
So let's
Yeah.
let's load up the notebooks on JuliaBox.
Okay. Anyone who doesn't want to deal with installation issues, this is your tutorial. Okay.
Let's see. Okay, so on JuliaBox, if you've used it before or if you haven't, just click on this sync tab, and under Git repositories, let's see where it is. The repository is JuliaOpt / JuliaCon - 2015. So you should just be able to copy in that URL, click tab, oh yeah, okay, just click the plus, click on this sync, oops, wrong button. Do you have to sync with the, yeah, that should be fine. You may have to click the sync button, and then when you go back to iJulia, you'll have a little folder there, JuliaCon, convex, load up the first notebook, and that should be good. The packages should already be there. Which ones? Oh, okay. If you do need to install the packages, just open up a new notebook.
This is 0.3.
I'm
going to have to update metadata.
No, this combination should be okay.
Okay.
It should be. Let's skip the gadfly. Oops.
Sorry.
Oops, that's wrong. Okay, so any trouble getting notebooks running on JuliaBox? Good? Okay.
Are people on Julia? Anyone who's not on JuliaBox and okay with the notebooks, raise your hand.
No?
Sorry.
Okay.
People who are still having problems, raise your hand.
Okay, I'll come up with it.
Executing the first second block with some squares to match one.
Please put an underscore between sum and squares. That's a typo. Okay. Okay, good. Okay, so we're gonna continue. Okay, so if I try to say x squared is less than or equal to the sum of y, I don't get any warning signs because x squared is convex, and having it be less than or equal to an affine thing is perfectly okay. We're going to see sort of some rules for understanding why that would be a little bit later. But if you draw yourself some pictures, you can convince yourself that the feasible points that obey this, the set of feasible points is a convex set.
Could you draw that picture?
Sure.
I don't understand what's going on.
Okay. Let's see.
Are they both vectors?
So how about this? I'm going to say, if I say x, let's see. No, so they're both scalars. right? So if I say x squared is less than or equal to the sum of y, actually I think the easiest way to see it is algebraically. So that's x squared minus sum of y is less than or equal to 0. And so how should I think about this? Well, unfortunately, I'm going to have to think about it in more than one dimension, which is harder to draw. And I don't have any erasers. But so here's how I would think about this. If y were 0, I'm going to suppose y is one-dimensional. If y were 0, then I would just have x squared. And now I'm going to make, so this is the x-axis along here. The y-axis is going to be along here. And if y were a little bit bigger, then I just take this shape and I move it up, right? And I move it up linearly. And if y were smaller, then I move it down, right? So I'm going to take this and I'm just going to move it through this dimension. So I'm going to keep having different shapes like this drawn at different places. But all in all, the thing is still curved up. And if I take any 2 points on it, it always lies above the value evaluated at any linear convex combination of points. So the whole thing is still a convex set. Equivalently, if you look at this, you can see it's still a convex function using the disciplined convex programming rules that we'll get to just in a second. Okay. On the other hand, x squared being greater than or equal to 1, I get another warning that it doesn't comply with the rules because the set of points that's where a convex function is greater than or equal to something, right, is off on the edges. So that's not a convex set because things like 0 is not in the set, but both 1 and -1 are in the set. So it's not a convex set. Okay, and problems. How do I construct a problem? Pretty easily. I just define my variables. I define my objective. I define my constraint or list of constraints. And then I say, please minimize that objective subject to that constraint or that list of constraints. And it forms a problem object for me and tells me a little bit about the convexity of everything that's inside the problem. Then I can solve the problem, ask for the status, and then I can also ask for the value of the variable. So I can say x.value, and it tells me that the optimal value is 0.2499, or I'm going to guess it's probably 0.25. But there's always some rounding error that you're going to have in the solvers, some floating point error.
But you haven't given it any data.
I have given it data. Actually, no. I mean, the data is things like 2 and 1. Okay. Yeah. Yeah.
So what exactly is a solver?
So this is using the SCS solver by default.
What is a solver?
What is a solver? A solver is something that knows how to take a problem in a very concrete mathematical form and find the solution to that problem. So the SCS solver knows how to take a problem in conic form and find you the x that maximizes that linear function subject to those affine constraints and those conic constraints.
Yeah, so it's the software that implements the optimization algorithm itself.
Yeah. So if I wanted to, so you know, here if I wanted to use a different solver, I can type using a different solver. Ecos is another open source solver, and I could type ecos solver and load ecos. Oh, and kill the kernel. Great. Okay. I'm going to restart the kernel then. Okay. As I said, we don't control the solvers. But ecos should in general work. I'm not sure why that happened. Any questions while we're waiting? Yeah.
Conceptually, you should explain that
Yeah.
what it's done is it's found a value for x and a value for the four values of y.
Right.
Which I know you're going to show in a minute, but
Yeah.
it's not just the objective value, but that objective.
Right. Exactly. So it finds the point that is feasible and minimizes the objective. Right. So it finds values for all the variables. Yeah. Yeah. So for example, right. So I know the value of x. Oh, and now, right. Yeah, so I've just solved this problem from above where x is larger, and so I have each of these, right? This was the x that corresponded to that non-negative least squares problem. So it turned out only 2 of the coefficients were positive, and the rest were about 0. I can also evaluate expressions directly. So I can do things like evaluating the objective. Now, this problem hasn't been solved. Just go back to... Yeah. I'm going to change it to this problem. OK, so now I have objective and constraint defined. So these are both sort of somewhat complicated expressions. But I can evaluate them by typing evaluate. Oh, but I haven't calculated the variable yet, so I need to solve the problem. Now I've solved it to optimality, and now I can evaluate the objective. OK, so there are a number of problem variants. So instead of saying minimize my objective subject to the constraints, I could also have asked to maximize it, as long as the objective were a concave function. I could also have just asked to satisfy the constraints if I don't have any objective that I'm trying to minimize or maximize. OK. So now I want to go through an example about sort of why you might actually use something like this before discussing rules that preserve convexity and sort of understanding how the package works a little bit better. So here's the example. It's an example that comes from neuroscience. So here I'm going to make sure that you've loaded all of these packages. I've already loaded them ahead of time. So I think all of them I think they should all be installed on JuliaBox, but if not, you can package.add them. OK, so here's the problem. It comes from neuroscience. Diffusion. So you can use a technique called diffusion tensor imaging to figure out at each little chunk of brain which direction is water most able to flow. Which direction is like water and blood and stuff most easily able to flow. That's probably the direction in which you have more white matter sort of connections flowing in that direction in that little chunk of brain. Okay, so over the entire brain, you can figure out which direction is are there more white matter chunks flowing? Where is the wiring? Which direction is the wiring pointed? And you can try, so given all these little tiny directions, you can try to match them up. And what neuroscientists tend to do is just use these path following algorithms where they say, well, it goes this way here and it goes this way here. So maybe it goes this way and then this way. And they sort of follow that through the brain. So they come up with a number of putative paths. And then they want to figure out which of these putative paths are actually real, which one actually explains sort of the global structure of the flow that I'm observing in this brain using diffusion tensor imaging. So one way of writing that is to say the following. So I'm going to have this vector B that's going to represent the amount of flow observed at every voxel in each direction. And the columns I'm going to have a matrix A, and the columns of it are going to represent possible fibers that go through the brain. So for every fiber, that fiber is going to tell me every voxel it passes through, that's the direction that blood flow will be going, that flow will be going in that voxel of the brain. And my job is to figure out which of these fibers are actually real and how thick they are. The thicker they are, the more flow is going to be going through that fiber. OK, so the way I'm going to model this is to say that I'm going to choose widths for each of these fibers, and that's going to be in a vector W. I'm going to multiply them by the mapping between the width of the fiber and how much flow is going in each direction in each voxel, and that's going to tell me the flow that I'm going to observe in that voxel. OK. And often the data is extremely large scale, so often we'll have like a data that has about 1 million different voxels times directions, and maybe 500,000 possible fibers that are traveling through your brain. OK, but we're gonna try solving a really small problem just so that we can play around with it really quickly. OK, so now we've got our A and our B, our observations and our putative fibers. Now, what do we want to do? We just want to find reasonable widths for the fibers that plausibly could have produced the data that we saw. And our job is to figure out what it means to be reasonable and what it means to be plausible. OK, so for example, reasonable widths. Well, a width of a fiber should probably be non-negative, because I don't know what it means to have like a negative fiber going through your brain. They also probably shouldn't be too big, because we know sort of certain constraints on how large fibers usually are. So I would be very surprised to find a fiber that was extremely wide. And I don't think there should be too many fibers. I think a lot of them should actually be 0, because I don't actually think you have 500,000 going through your brain. I think that a lot of these paths traced out were just total garbage, and a lot of them should be 0. What about possible errors? Well, maybe they shouldn't be too large, right? I don't think the machine is making like huge errors. I think it's making a lot of small errors. And maybe I even think that the errors are distributed, like there's some sort of sum of IID variables that's creating my error. In that case, I think the error should be Gaussian. And if I think the error is Gaussian, then the negative log likelihood of the Gaussian density is a quadratic. So I might think that fitting a quadratic to the error would be a reasonable proxy for how unlikely it is to have made that observation given those widths. Okay, so here's how I'm going to describe the problem. I'm going to say my widths are a variable of length n, so 1 for every possible fiber. And my errors are just the difference between a times the widths minus b. Okay. And it can tell that the errors is a nice affine expression. So my optimization formulation is just to minimize the implausibility of the errors plus the unreasonability of the widths. And I'm very sure the widths are non-negative. So I'm going to put widths greater than or equal to 0. Okay, so if I expect Gaussian errors, then to maximize the likelihood of the errors is the same as minimizing the negative log likelihood of the errors, which I can write like this. And I impose the prior. So here's how I would construct that problem. I would say the widths are my variable, errors are a times widths, and I'm going to minimize the sum of squares of the errors subject to the widths being greater than or equal to 0. This is my model number 0, okay? I'm going to solve this, and I get an optimal value of 41. And this is the histogram of these widths that I found. So some of them are close to 0, and some of them are a little bit bigger. And I want to know maybe which constraints are active. For which of these fibers would I have wanted to impute a negative width, but I stopped because I know that that's not possible? And the answer is that I haven't consigned. Oh, so if I want to know that, then I'd better define a variable called constraint, or called anything I want. That's equal to, that tells me which widths are greater than 0. And then when I solve that, now constraint is going to have a value called dual. And that dual variable is going to tell me if you've, I'm not going to go into duality because it's going to take longer than we have, but it tells me which constraints are active, so which ones are actually sort of keeping the solution from going negative. And it tells me the first one and the 8th one would really like to be negative, but I'm not allowing them to be. Okay. Now, what would happen if I added quadratic regularization to encourage small widths? This is sometimes called Riggs regression. And it turns out it's very easy for me to see what happens for different values of gamma as I encourage, as I penalize you more. I say, I think very large widths are extremely implausible. So we're going to run this cell. And as I say, if I said, oh, no, small widths, no problem, fine. Then I get some values of x that are as large as 1. As I increase gamma, interestingly, I get one that's gone up, but a lot of them have gone down, have gotten a lot smaller. And as I increase gamma more and more, I get smaller and smaller and smaller widths. Okay, because it's saying I really don't think large widths are likely, so I'm going to force them to be small by telling this optimization problem that large widths are implausible. Okay. On the other hand, like almost all of these widths are non-zero, right? Almost all of them are positive. And that seems really unlikely to me because I know how these paths have been traced, and I think a lot of it is junk. So I think a lot of them should be 0. So what I'm going to do is I'm going to change my regularization. Instead of regularizing with the 2 norms squared, I'm just going to pick a p norm. That's the, just to say what I mean by p norm, I mean the sum of xi to the p all to the 1 over p. And I'm going to let p go between 1 and 2. Okay. So what happens is I change p. So here I've set gamma to 1, so that's how much I care about the I'm weighting the relative implausibility of the widths versus implausibility of the errors. And if I send p to 2, that's what we had before, and a lot of the widths are non-zero. As I send p closer and closer to 1, I find more and more of them are 0 until I get to 1. A lot of them are 0, and now only 3 of them are non-zero. Maybe I like this model better. Yeah, questions?
We're having a problem running the notebook.
Okay.
The variable constraint is not defined.
Yeah. So that was something that I had to add. Yeah, there was another typo up there. So if you define, so in order to access the variable constraint, you're going to have to actually name it. So if you say width greater than or equal to 0, then you'll have access to that. Yeah. So. Yeah, and you're going to need to change in the problem, put in constraint. Oh, there we go. Yeah.
When you vary P, is it the same as what's called as elastic net, which is a...
No, so elastic net is a little bit different. We can actually do that one too. Let's see. So elastic net, let's do it. Yeah, let's do it here. Okay, so I'm going to do a 2 norm. So elastic net is a 2 norm plus a 1 norm. So for elastic net, I would have to do plus gamma times the 2. This is the okay. Elastic net is the sum of the squares of the widths plus another penalty term. So lambda times the 1 norm of the widths. Okay, I could use lamb. Okay. And why don't I try varying lamb as well? I do need to put in a plus. Thank you. Okay. So that would be elastic net with a non-negativity constraint, and let's see if I've typed it right. Of course, sum of squares doesn't need a 2. Okay. Oh, so this is kind of fun. Okay, so as long as lamb, so the bigger lamb is, the more zeros I get. So the 1 norm is really encouraging sparsity. If I decrease lamb, then I get a lot less sparsity. But even if I have a very small lamb, I don't get very much sparsity. Okay, so if I want sparsity, I better have a decent lamb. Now, what does the gamma do? This is the one that's regularizing the square. And this one is really controlling the size of the ones that are non-zero. So as I increase it, it's making them much smaller. And that's because the 2 norm cares a lot more, the quadratic cares a lot more about very large values, is very angry about very large values. A 1 norm doesn't care as much about large values, so it controls the size much more slowly. Yeah?
So you did still solve all that grid now, your solver?
Yeah, so I'm resolving. Every time I move this slider, I'm resolving the problem. And this is why I chose a very small problem. Yeah, okay. No, it's using this one is using a first order variable splitting method called ADMM. So I'm using the SES solver. The method for the SES solver is described in a paper that you can find from the SES website. It's a cute algorithm, but yeah. I could solve it using gradient descent. It would probably be slower. Yeah. Okay. But I can also solve it for a bigger version. I mean, there's not very much to see here, just that it takes longer. Okay. Gradient descent, I would expect to take longer. I mean, it depends on a lot of details, right? It depends on step sizes. It depends on, okay. I think yeah. Yeah.
So is the picture I should have in my head
Yeah.
that I have like a conic thing in high dimensions
Mm-hmm.
and looking for the minimum?
So the picture that you should have in your head. So when you have a problem in conic form, here's what you should think of. So remember, what were we doing? We were minimizing a linear function subject to affine constraints and conic constraints. OK, so the first, well, I can use, I think I can reuse part of this picture. OK, so what do I have? I want to know that my decision variable is inside some cone. OK, and I also want to know that it obeys certain affine constraints. So I'm looking for a point that's in the intersection of this cone with these affine constraints. And subject to that, I'm going to have some other linear function that I'm going to be trying to maximize. So here I could draw my linear function I'm trying to maximize. And I want to push that line up as far as possible while I'm still in this feasible set. So here I would push this line up until I get, and the maximum I'm going to be able to push this line to without getting outside of the feasible set is going to be right here. So this is going to be my solution. OK, so you can see that actually like having that structure makes it much easier to analyze the problem. So actually what SES does is effectively it projects onto these affine constraints and then projects onto the cone and then projects onto the affine constraints and projects onto the cone with a little bit of cleverness involving duality to make it converge a little bit faster. So having an algebraic description of that cone and of the affine constraints is essential so that you can actually perform the projection efficiently. Yeah.
Will this let us do a zero
Hmm?
norm? Will it let us do a zero norm?
Zero norm.
Oh, no. So zero norm is not convex. Anything below, you know, p norms. What do they look like? Here's the p norm of a scalar. The 1 norm looks like this. The 2 norm is going to look like this. And the p norm for p less than 1 is going to look like that. OK? Not curving down, still curving up. So that's not a convex function, because if I take 2 points that are on the graph and I connect them by a chord, that chord lies below the function. So it's not convex. And if it's a zero norm, it's like the worst case of all. It goes straight up and out. So that's not something you can solve using these methods. You can solve those kinds of problems in JUMP. Well, you can definitely solve them in JUMP. You can also solve them in convex by using integer or binary variables. But you sort of lose guarantees of convexity, and you have to pass it to an integer programming solver instead. So not by expressing it as zero norm. So did that clarify?
Yeah.
OK, good. OK. So yeah, I wanted to describe quickly OK, how you can tell if a problem is convex. So I think I'm going to do this, and we're not going to do the time series example. But if you want, you can look at the time series notebook on your own. It should be kind of fun. It's a little bit more of an in-depth example about how you would do some model fitting for time series. And it's also in that GitHub repo. OK, so we only solve convex optimization problems. So how is it going to tell that our problem is that the problem is convex? Remember that a problem is convex if convex combinations of feasible points only get better, right? So a convex combination of feasible points has to still be in the set of constraints, and it has to have an objective value that's at least as good. So to verify convexity, all that convex.jl does is it relies on its ability to verify to tell the convexity of an expression. So as long as the objective is minimizing a convex expression or maximizing a concave expression, we're good. As long as the constraints are convex is less than or equal to something, concave is greater than or equal to something, or affine. Yeah?
The combination of 2 points can only be better than the worst of those points, or better than either of those points?
Better than the average of those points.
Okay, got it.
The average of the values. So it's exactly this picture about chords. OK. Yeah, good. OK, so then the question becomes, how do we tell if an expression is convex? The answer that convex.jl uses is a technique called disciplined convex programming. It knows the vexity of variables, which are just affine, and then it knows how functions transform the vexities of their variables into the vexities of their outputs. And there are just 4 rules, effectively. F composed with G is convex if F is convex and increasing and G is convex, or if F is convex and decreasing and G is concave. And F composed with G is concave if basically the opposite conditions, f is concave increasing and g is concave. I don't have enough time right now to give intuition for what's going on here, but basically you can get this if you had smooth functions via the chain rule, and the argument for non-differentiable functions is not much harder. If you wanted to play around with this, a great place to go is dcp.stanford.edu, which allows you to type in any expression here and see why it's convex. So something like abs of pos of x. It's going to tell me that this is convex because it's composing abs with pos. It tells me the signs it's able to infer and the slopes of the variables. So it's a system very similar to this that convex.jl is using. And you can type in more complicated expressions if for some reason if you can't figure out why it's convex or not.
Where is that again?
dcp.stanford.edu. It's linked right here in the notebook. Yeah. Okay. And then in order to tell whether a function is concave and increasing or concave and decreasing, if you can't figure it out yourself, all of that is documented in our documents, because that's one of the sort of most important things for you to know about the function. So we can tell you what the convexity of the function is and whether it's increasing or decreasing in its arguments. And this is basically, these are the combinatorial tools you need to understand in order to understand how to put things together into convex functions. Okay. So very quickly, I can say how convex.jl works, and then I'm going to turn it over to the jump tutorial. The basic idea is first you construct this abstract syntax tree, sort of to understand which functions are composed with others in order to build up your expressions and thereby to build up your problem. It's going to take that abstract syntax tree and parse it to this canonical conic form and then pass it to a solver that knows how to deal with these conic forms. Okay, so when you're doing this operator overloading, it's constructing an abstract syntax tree, and you can think of the form looking something like this. If you ask for an expression like pos of sum of x plus 1, it's going to do the sum of x, it's going to do the positive part of that, and then it's going to add that to 1. The way it parses to a canonical form is first to introduce new variables. It's going to introduce a new variable for every function that you've used. So one for the sum, one for the positive part, and one for the addition. Now what I do is I relax the convex constraints. So even though I've said v2 is equal to the positive part of v1, now this is a convex function, and this is an equality constraint. So that's not allowed by the rules, so I relax it to something that is allowed. v2 is greater than or equal to the positive part of v1. And as long as the compositions I've used have obeyed the DCP rules, the discipline convex programming rules, then the solution to this set of inequalities is going to be the same as the solution to that set. So that's the reason why we need disciplined convex programming. And then the next thing that I do is I canonicalize this form. So each of these atoms knows how to turn itself into a set of conic constraints. So sum turns itself into this affine constraint. Positive turns it into this set of v2 is greater than or equal to the positive part of v1 turns into this set of conic constraints. One affine constraint and two cone constraints saying that v2 and v4 are both in the positive orthant. All of their entries are greater than or equal to 0. Okay, so now I have this collection of affine and conic constraints instead of the original function representation. And so now I just have to gather these up and assemble them into matrices in order to have a standard conic form for the problem. And at that point, I can pass it to the solver. So in code, this is what I would do. And the conic problem is an internal function you won't need to call, but I just wanted to sort of allow you to sort of see where the transformation is going. So you get this C, this A matrix, and this B matrix. And then it'll tell you what cones your variables are in. So I've got 2 non-negative variables and 1 0 variable, which corresponds to that guy and then these 2 non-negative ones. Okay, and then it passes to a solver. You can use any solver that's in math_prog_base. You can always see the list of convex.jl operations to figure out what cones you're using, and then look at the list of solvers in order to see which cones that solver can solve. If you try to solve a problem with a solver that doesn't, a problem involving codes that the solver doesn't understand, you'll get a warning error, and you'll go and you'll find which solvers understand those codes. SCS understands all the codes that convex parses to. So SCS is always safe, but sometimes you'll get faster solve times with different solvers. Okay, so that's a sort of basic overview of convex.jl. Any questions for me before we move on to jump?
Can you comment about the applications that people use it for?
Sure. This is a large set. So I think really the best place to look is the collection of notebooks that's on. Okay. Let me restore that up. Okay. The best place to look is the collection of notebooks that's in the convex.jl repo. And you'll see a whole bunch of examples. So, I mean, the general sort of kinds of things that you might use this for mostly are either model fitting problems. So you've got some data, you understand a little bit about how the data was generated, and you have some prior about what the parameters generating the data might be. And you want to find the parameters that best fit your data while conforming to your prior. That's sort of one very general class of problems. Another very general class of problems are the decision problems. So you can imagine you have a model for the world, you have a model for how your actions affect the world, and you want to choose the best actions to minimize your cost or maximize your profit. Subject to your decisions being feasible, ones that you can actually undertake, and that they obey the laws of physics and things like this. I think the jump tutorial is going to include many more problems of that kind. In some ways, this global connectome neuroscience problem was more of the model fitting kind. But oftentimes, the work of an optimizer proceeds in these two stages. First, you fit your model. Right, you try to understand, what equations are governing your world, and then you try to take the optimal actions given this model of the world. So both of these steps are optimization problems. Yeah.
Is it possible to communicate information about termination conditions from convex to the solver?
Yeah. So each of the solvers in general might use different. Have different optional arguments that allow you to set things like the maximum number of iterations or the tolerance that you want to solve your problem to. Or verbosity settings, things like that. All of those can be found on the individual solvers' GitHub pages. So you would go to things like scs.jl if you're using SCS. You would go to mosaic.jl if you're using Mosaic. You would go to ecos.jl if you're using ecos. And you would be able to find those options there. All of those can be passed through when you call the SCS solver or ecos solver or Mosaic solver. You've got some parens there that you can put the arguments into. Any other questions? Okay. Yeah, so I in particular recommend this time series example that I wanted to get to, but I want to leave time for jump. You can see we have logistic regression, we have control problems, we have a binary knapsack problem, so figuring out how many tasks you can schedule. Yeah?
Is it expected that when you have one of those tools to add manipulate, and you're going to solve 50 problems within there, that it's going to take a long time?
It depends how big your problem is. So if you're gonna put something inside an app manipulate, I would suggest that you solve the problem first before putting it in an app manipulate, and then move it around. But actually,
You have a couple in the time series example, and it's just painting the machine.
that's interesting. So interesting. So in my version of the time series example, those were going. They aren't hyper fast, but they took about half a second to solve.
I've been waiting 10 minutes.
That's a lot slower. So yeah, mine are going in half a second. So you might want, so I'm using a slightly newer version of SCS and Convex. You might want to update metadata and pull again. Okay. I'm not sure. I can come, look at your particular install. It might, okay. Yeah, there's some wonky stuff going on with SCS. I would expect I would expect that the time series examples will run in half a second within a couple of days, but we're working on some installation issues with SES.
So I'm guessing the unknown error, the status is a time error.
No, so I have a max iter's thing at the top so that it doesn't run too many iterations, and that's what's creating the unknown error.
Yeah, I'm guessing it's hitting
Yeah, so it's hitting max iters, yeah, but it's a good enough solution that I don't care. Yeah. Okay. So I think we're going to move on to the jump tutorial. Yeah. Good. Okay.
Let's do some jumping.
Do some jump. We've been sitting still for like over an hour and a half now. It's time to jump. Okay.
Not any ones that you should use right now. It's not so much a comment on Julia, just on the difficulty of writing
solvers.
a truly competitive and robust. I'll do it on my own. I got it all set up.
Okay. Yeah, so I'll take my laptop back. Good. I've written some, but not not the fastest ones.
All right. So we're gonna now switch to jump. So if you're using JuliaBox, everything should just work without installing any additional packages. Everything is available. However, because I was apparently using Julia 0.3.7 on my machine, when you open the notebooks in JuliaBox, it'll say something about kernel not found. Do not click the bigger of the two buttons it presents you, which basically is like the give up button. Just click Julia 0.3.9 and click OK. Everything will be fine. But I clicked the big give up button like twice because it's just like the big button. So avoid the big button. Let's see. And then I should be able to do this little thing here. All right, so we're going to do 2 examples of jump, very different examples. I'm going to be running them locally, but it should work just fine. All right, let's clear all the output and make it big. Get rid of this crap and make it bigger. And nothing's on the screen. And I guess I should do the old mirror display thingamajiggy. Arrangement, mirror displays. All right, okay. Whoo-hoo. There we go. Now, are we too big? Maybe. No, too big. All right. Okay, let's optimize. So, the first example I'm going to show you is motivated by compilers. It's a kind of a compiler problem. So I've got some operation that I define, and the operation I'm going to be thinking about in this example is a 4-element dot product. My ASCII art's ruined. All right, there we go. So we're talking about 4-element dot product. So I'm taking 2 vectors of length 4. I'm taking the dot product of them, inner product of them. And to do so, I'm going to tell you up front the instructions that need to be run and in the order they need to be run in to calculate this number. So I need to multiply each element pairwise. And then I want to add the result of the first 2 multiplications together, add the result of the second 2 multiplications together, and then add those 2 sums together. So I'm calculating the dot product in a kind of mechanistic 2 elements at a time way. So I give you that, and I say to you, tell me what order to run those operations in, subject to some constraints. And the reason we're doing this is that CPUs do not run every instruction one by one and wait for the previous one to finish. They have all sorts of magics going on with pipelining and so on. And it's the job of a compiler to basically take advantage of that and tailor the code that is generated for the realities of a machine. Now, of course, it goes way further than this. So I bet a modern CPU can probably do this in like 2 instructions, like a 4-element multiply and then a 4-element sum or something. We're just going to assume we have these simple primitives of multiplication and adding, and we're just interested in scheduling them. So while this is all about compilers, it's actually a very general problem of just how to schedule anything through some sort of system that has precedence constraints. So this could be a manufacturing process. I mean, in a sense, it's the same as like scheduling people. So the kind of optimization problem we're going to cast this sort of optimal instruction sequencing problem as it's going to be a binary optimization problem. And what that means is that all the decisions are either 0 or 1. I'll tell you what the exact decisions are in a moment. They're all 0 or 1 decisions. And we'll be able to express all the constraints and the things we want to have about the solution all as linear functions of these 0 or 1 decisions. So we would say this is an integer linear optimization problem. And the solver that I believe it'll use by default on JuliaBox is the, oh, I lost my little full screen, is the CBC solver, coin, branch, and cut. It's open source. And at the end, if we have time of this notebook, I'll demonstrate the limitations of open source solvers. So that's probably a good shout out to the companies that make faster ones, because it's a tough problem. All right, so this is my sort of directed acyclic graph of operations, and this defines the precedence constraints we have in these operations. And now I'm going to set up the rules for my hypothetical CPU. So time is going to be discretized. So everything's going to start, on a tick, 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 tick. I can only start one operation at a time. I can only run, so each operation takes 3 units of time to run. So if I started at time 1, it'll be finished at the end of time 3. And at time 4, I could start something new. But I can run 2 things at a time. I can actually run 2 multiplications at a time. And I can run 2 additions at a time. And those are independent totals. So I've got 2, sorry? I heard my echo. Sorry, I thought someone asked a question. So I got 2 multiply units and 2 addition units, you can imagine. And they can all be run parallel. And that's the rules. And that's pretty simple. So you may be thinking, Ian, come on. Like, I can just see what to do by looking at it. And I would hope you can. But the point is not to teach you how to make an optimizing compiler. It is to teach you how to make a model and jump. And then we will push it a little bit in an extension. And once you start adding more interesting constraints like registers, like which registers are being used for what, and you've only got so many, and you've got to stick them somewhere, you won't be seeing it so easy. But we won't do that because that's probably a master's thesis. OK, so let's get started. So here's what I'm going to do. I'm going to OK, so we're going to be modeling it as a binary optimization problem, like I said. And we're going to set up some groundwork. So I'm going to set a maximum sort of time horizon. So this operation is going to be able to be scheduled in 20 time units. The length of instruction I'm going to fix is, I'm just going to call that L. That's going to be 3. And the max instructions of a certain type I can run at a time, I'm going to call that C. And I'm going to make a list of all the operations, ops. And I'm going to use Julia symbols. So that's what a colon means. And I got mol of AE, mol of BF, mol of CG. And there's going to be 7 of those. So the last one is going to be add all, which is sort of off the end there. So what we're interested in is when each of these 7 operations starts. So I'm going to load jump, which you should have installed. If you're on JuliaBox, you have to install it yourself otherwise. And I'm going to make a model. I'm going to call it M because single letter variable names are the best. And you should always use them in production code. It saves valuable memory. So I've got this commented out lines here. So when you do using jump and create a model, it doesn't really explicitly pick a solver right then. What it does is it waits until you hit solve, and then it looks at the problem you've got and picks the best available solver, or the most appropriate, an appropriate solver, not necessarily the best. And you can choose to override that by passing a solver as a keyword argument. You have to load the package name explicitly. It will automatically load the package if you don't specify one. But if you want to specify the solver, load it like this, and then you can pass things like a common one I pass to Garobi is output flag equals 0 because it silence the output. But we're going to be using just the default solver that is picked. So you'll need a solver of some kind installed, but JuliaBox will have CBC. And then let's get started making the model. So the very first thing I'm going to do is define a variable using the def var macro. So this is a variable not in the programming sense, but in the thing I want to optimize sense. So it's a little bit of a terminology overload when it comes to programming. It's both. I mean, that's the thing. So start_at is a Julia variable, and it refers to decision variables in the optimization problem. So we're really semantically overloading here. But what I'm doing here is I'm creating a variable called start_at. And you can think of this as kind of a non-standard array of decision variables. And it's indexed by two things. It's indexed by ops. Recall, ops was this array of symbols. So lesson number 1, jump variables can be indexed by up to an arbitrary number of dimensions and can be indexed by arbitrary sets. So we're indexing by symbols for the first dimension. And the second dimension is going to be time, 1 to t, just a range. And so that variable is going to be a binary variable, bin. And it says if we start this instruction op, instruction op at time t or not. While we won't be doing that right here, you can put more interesting things like less than equal to 5, and it's just continuous, and so on. But we're going to cover that in the next example where we do, it's a continuous problem. But here, everything is going to be binary 0-1 decisions. So I'm going to execute this cell, and absolutely nothing will happen, which is really good, because nothing is supposed to happen. So now we have a model. It's got some variables. It's got 7 times 30 of them, I suppose. And we can refer to them using start_at. And you can immediately start making some observations about the problem. So something very obvious is that you shouldn't be starting any instruction more than once. Remember, we actually made one variable for each operation. So each operation starts once. So a natural constraint to add is a constraint enforcing that each solution starts once and once only. So I'm doing a loop over every op in my list of operations, and I'm adding a constraint to my model M that says the sum of these variables for this given opt across time has to equal 1. Now, since each decision is a 0 or 1 variable, this is saying that one of those variables has to be 1. It's the only way to satisfy this constraint. If 2 of them can't be 1, and none of them can be 1, one of them has to be 1. OK, that's our first constraint. Pretty intuitive. Now, as we go through this, you might want to think about what really is the core minimum set of constraints required, because I have a feeling that this is actually not required because there's no incentive for the optimization model to start an instruction more than once. All we require is that the last instruction starts, and then everything else should probably flow from that. So that's something to think about. Usually, redundancy in constraints does not necessarily hurt too much, and in fact, it can help somewhat counterintuitively. But that's the vagaries of NP hardness, I guess. So, OK, the next constraint we're going to add is that at most one operation can start at each time. And we definitely need this one. This one's critical. It's not going to do this by itself. In fact, it wants to start everything right at the start. Or it wants to start all the multiplications simultaneously. So we're going to add a constraint that basically says it's kind of the same as the previous one, except now we're looping across time and summing across the operations. So here we go, and we see for all t in 1 to t, sum across the starting variables across the operations this time for a given t, and that has to be less than or equal to 1. We can start at most 1, but we can choose, and may in fact have to, not start any at a given time. Now, at this point, I want to pause and briefly look a little bit closer at this suspicious-looking curly brace here, which you may be looking at and being like, Ian, you sly dog, what are you trying to pull? And what I am trying to pull is we have embedded a language inside Julia. And what we have done is we have made a more powerful sum. And the thing is, it's kind of like a Python array comprehension or a generator. So what it lets you do is sum over multiple index sets in this kind of notation. So this is very Pythonic. So if I wrote 4, it would be pretty much Python. And perhaps even more importantly for us is that you can put a semicolon and do a condition. So I could say only sum over the t such that t is even. So this is helpful when you've got some kind of like guard or filter on your sum, which is a pretty reasonable thing to have in the kind of problems that we look at. We won't actually be using that conditional feature in today's examples. And I don't end up using it too often. If you construct your index set right, it doesn't usually matter too much. Remember, if you have like an n squared number of things you could possibly index over, and you're iterating over all of them and checking the condition for each one, that might be a little bit slower than just thinking about it carefully and explicitly stating what you're indexing over. But that's an aside. OK, so we're studying one operation at a time, studying each operation once. And as you may imagine, there was many possible ways we could schedule this. And I'm just going to fix a schedule that starts with doing the first multiplication first. Because I could imagine a completely symmetric solution where I start the last multiplication first, and then there's multiple solutions to this problem. I'm just going to fix one so we're all kind of on the same page, because due to floating point magics, maybe we might get different ones. So I said floating point magic, but note the problem's all 0 or 1. So I don't want to get into why that happens, but it's not our fault, it's just math. All right, so that was actually the easy part. That was like the logical part. And here's like the biggest conceptual leap, and that is the precedence constraints. So what are we saying? We're saying that we can't. The way we're going to model it, and there's multiple ways we could model it that are all equivalent, is that we're saying that if we start this mole at time 1 and start this mole at time 2, the first time we can start this add is L time units after the second of these moles starts. So I start the first multiplication at time 1. I start the second multiplication at time 2. This is going to be running for this one, and it's going to be running for this one. This is time in the x-axis. Let me pull that down. So this is going to be running for this one and this one. And this was the first time I could start my addition. I can start it here. And the way I'm going to turn this into a linear constraint is I'm going to say that this variable cannot be 1 unless this one appeared before this time, and this one appeared before this time. So the two ones that this one needs to start have to have happened at least L minus 1 time units before. And the great thing about that is saying that there's a 1 somewhere in here and a 1 somewhere in here is just equivalent to saying take the sum across all time back here and take the sum across all time back here. And if that sum is at least 1, that means you had a 1 somewhere in there. So that constraint would mean that if this was 0 and I actually started it here, so this one happened, which is good, but this one didn't happen. So the sum across time from this time backwards is 0 and 1. And I'm going to say this number can only go up to 1 if this is at least 1 and this is at least 1. This one's not 1, so this one can't be 1. However, this one would be OK, because that's looking from this time slice back, and we're OK to go. So let me try and write that as a linear constraint. And being able to write things as linear constraints is kind of the art of this kind of integer modeling. And it's a little bit of a practice. It's basically practice. But I find it very satisfying. I don't know about you guys. It's kind of like beating the system. All right. So here is how I'm going to do it. I'm going to loop across time from 1 to t minus L. I just did the t minus L because we can't start anything like right at the end anyway. But we don't really need that. And the first two constraints are going to be exactly what I just described. So the add ABEF, so the add that uses the result of the first two multiplies. So for each possible start time t, start at for add ABEFT is less than the sum of the start ats for mole AE across all times s from 1 to t minus L. So that is saying this cannot be 1 unless the sum of all these is at least 1. Or rather, this is less than or equal to the sum of all this. We also need to say a separate constraint saying this is less than the sum of all this. That means that both of them have to have a sum of 1 for us to put it to 1. Because remember, The optimization problem is trying to start everything as soon as it can. So we're basically trying to tell it when it cannot start, not when it can start. Which, yes?
You make that in one constraint and say that the sum has to equal 2 for both?
No, but I could do the following. I could say it's less than equal to the sum of the 2 divided by 2. So what that would mean is if I had only one of the conditions, it would be the left-hand side is less than 0.5, and because it has to be 0 or 1, therefore it must be 0. So I could do it in one constraint if I then kind of normalized it. Otherwise, if I just took the simple sum of the 2, only one of them would be 1, and then the right-hand side would be 1. I could put the left-hand side to 1. So if there's 2 equivalent ways to write it, it can either write as 2 constraints or combine the constraints but normalize by the number of operations it's dependent on. And it's a valid question whether one of the formulations is better in some sense in terms of how well it solves. But a nice thing about this is that, I don't know, yeah. It's some properties of what that translates to, like geometrically, that can affect how it solves. So you can try both. But I find this, personally, I picked this formulation because I like not having to divide by the number of operations. And then if you're OK with that, then the next 2 follow sort of directly from it. So we're basically saying, for each possible start time, look from L back to the start of time. And if you ever had the precedent start any time back then, you're good to go. So I'll run that. And then finally, let's have an objective. So we haven't actually put an objective on the problem yet. And the objective I'm going to use is to minimize the sum of t times the variable that says when the final operation starts. So if the final operation starts at time 10, my objective will be 1 times 0 plus 2 times 0 plus 3 times 0, 10 times 1 plus 11 times 0, and so on. And if I start the operation at time 20, I'll have an objective of 20. So the objective is essentially the start time, which I want to minimize. Again, it's a linear function, which is nice. And not just nice, useful. So I now have all the components I need for a first pass. I'm obviously missing something, and that is a constraint that you can't do more than 2 adds and multiplies at a time. But I'm going to solve what I've got. I made a little pretty printing function. So to solve the model, we call solve m. Sorry, I should go back. For set objective, you can put min or max here. This function here can be quadratic in the variables. And all these constraints can also be quadratic in the variables as long as they have to be quadratic. It can be quadratic in the variables. If it's not convex, good luck solving it. More heavy machinery required, but jump is agnostic to that. So this could be quadratic. I could have had, actually, there's no point squaring it because it's 0, 1, so I can't even pretend to demonstrate that. But I mean, 2. OK, now we're squaring it, so let's not do that though. Yeah, so I solve it with solve. You can choose to get the status back. In this case, the status was optimal. That's nice to know. I made a little pretty printer here. To extract the value of a variable, we use the getValue function on the variable. Pretty straightforward. The number you get back, even though it's a binary, is actually going to be a float because of how solvers work internally. So I rounded it so I don't have to do a floating comparison with 1.0, which would almost surely not work. And if it is 1, I print an S. Otherwise, I print an underscore. And here we go. Here's a schedule. So you can see it starts the first multiply at time 1. And then it starts this multiply down here at time 2. Starts this multiply, starts this multiply. And you'll see that A, B, E, F does not start until BF has finished. So BF is running for these 3 time steps. And then A, B, E, F can start. Now, this doesn't look right to me. But maybe it's because it doesn't matter. I would have thought it would want to do AE first and then BF, so I could start this as soon as possible. But maybe somehow it doesn't matter.
Not without the constraint on the number of processors.
We'll fix, yeah. We haven't done that.
Because right now you're doing one operation per
With 6, so it just does whatever it wants. Yeah, it doesn't matter.
10 operation.
Yeah, it has to get there in the end anyway. Yeah, so super trivial. So let's finish the problem. So
Can I stop there and just ask a question? So
yes.
Like you found one optimal solution, but there are equivalent solutions.
Yes.
Can you find them all?
So we did not explicitly provide a functionality to enumerate them, but there is simple mathematical things you can do to do it. So you can basically add a constraint now that says you can't give me that solution back again, optimize. And you can imagine basically saying, find the vector of zeros and ones that's at least distance 1 away from the current solution, like the Hamming distance, I guess, of it.
It's going back and modifying.
It's going back and modifying the problem. So the solvers do not themselves, they're not really designed to enumerate all possible solutions. So you kind of have to do it semi-manually. So it's easy.
And sometimes there can be exponentially many possible
Yeah.
solutions. So in that case, you probably don't want the solver enumerating all of them, right? And a solver that kept track of all of them at the same time would probably be a very slow solver.
Yeah.
Right, well, okay, so yeah, maybe I want an iterator solutions or something like that. But yeah.
Yeah. So it's not too tricky to like basically do it yourself. Just by adding a single constraint is enough to do it and then resolve. So with an integer program, there's like it's a little bit annoying that so integer programs do not hot start in a sense. You kind of have to do a lot more work even though you just solved it. But what we do the best we can, which is if you've just solved it, we will give the last solution to the solver, and it will use that as kind of like a known good solution, and I can use that to sometimes finish quicker. For other problem classes like linear optimization problem, linear programming problems, you can warm start. You can actually, if you make a small change, it might require a very small amount of work to get to the new optimal solution. So if you modify the problem with jump and then hit solve again, we will start if the solver supports it from that point. So you can very quickly solve like a whole set of problems as long as they're kind of like simple modifications.
So I'm very interested in that. Is the mechanism for that dependent on the underlying solver that you
The solver must support it. But I think all the linear programming solvers we support except maybe Ecos, maybe, I don't know. All the traditional, Ecos doesn't, but like Cplex, Gurobi, CLP, SCS, GLPK, I think they all support linear programming hot starts. Yeah, which is essential for some techniques. A constraint generation, Bender's column, vehicle, whatever. So yeah, we try and support everything the solver itself can support. Yeah. Okay.
One more question.
Oh, sorry, yes.
What is the status optimal? Does that mean locally optimal, locally optimal? How does it know?
It means, that's the solver's opinion. So in the case of an integer program, it means that it found an integer solution. So integer programs are solved by solving a series of relaxed versions of the problem. And occasionally it will find a solution that is like integer, naturally in a sense. And so it's since we're minimizing, the relaxation is getting our objective better than what is possible. And it's finding better and better integer solutions and they're coming together. And when it gets to a 1% gap, or whatever gap you set between the values of the two, it'll terminate. So it's not necessarily the optimal solution. It's optimal to tolerance. And that is like the status that is reported by the solver as optimal. But if you put like a time limit, it will return like user limit because it doesn't want to make a claim of optimality. It'll also come back with infeasible, unbounded. Those are the usual ones. Optimal, feasible, unbounded, or user limit. So let's just finish off this one by adding the more constraints. So I'm going to model this extra constraint about things running in parallel by adding a new set of variables. And the new set of variables is going to express whether the operation is running or not. So for each time in each operation, this variable will be 1 if the operation is running. So the thing we had before is kind of like the edge trigger, the up edge, and this is going to be kind of like whether it's how long it's running. So this one started at time 2, so start at for this operation will be on for time 2, and then this new variable I'm creating will be on will be 1 at this time step, at this time step, and this time step. And modeling it that way means it's very simple for us to then say, okay, the number of things that are running out of a certain type at any given time is less than or equal to 2. And that's why I like it. It's not the only way to model this. In fact, I'm pretty sure you can model this without introducing new decision variables, but it would be messier, and it's not clear that it's actually any better. So I'm going to define a new set of variables running, same format, op as indexed by ops. I don't actually have to explicitly provide a shorthand, but I find it nice visually. It's also got a utility in that if I provide, so let me pretend this is not binary for a moment. I can go less than or equal to t. And each of my variables will have an upper bound that's based on its index. And this can be anything in here. This could be a dictionary lookup, a data table lookup. So you can provide a separate bound for each variable in a set of variables. And that's why you'd want to provide something to index over, because of course if I don't put t equals there, it's not going to know what to put here. Basically, this is a macro, but the macro is conceptually simple. It's essentially expanding out to some for loops and some function calls, and it's not doing anything too mystical. It's just a very shorthand way to make a kind of a more abstract container than the usual matrix or dictionary. It's a little bit of a dictionary, a little bit of an array. So, okay, so I've got this new variable. I need to link it to my other variables. And what I'm going to say is for each operation and for each possible start time for each operation, and for each of the L units of time after that operation start time, if it running should be greater than or equal to the start. Running at time s should be greater than or equal to the start time variable at time t. So if start at is 1 at time 5, running op will have to be 1 at times 5, 6, and 7. And that's all that constraint is saying. So we're looping over start times for the operation, and then the times that would follow on from that. And with that, we're actually pretty much done, because then to say I'm just making a separate little index here for the sake of code beautification of the multiplying operations and the addition operations, I'm just saying for each time, the sum of running instructions for each operation class at that time is less than or equal to c, which is my parallel count. And we are now fully modeled. I would print the model, but it's actually grown quite big. There's, what is this? 7 times, there's hundreds of variables, and there's actually many constraints. We do support model printing, and it's kind of pretty in LaTeX. But unfortunately, for anything interesting, it's usually just too big to fit on a screen. So I won't try and do that now. I'll solve it, and it solves pretty much instantly. And here's the solution that I got this time. So we're starting A at time 1 and B at time 2. They run for 2 additional time units after that, so 3 in total. I start D as soon as I can. So I couldn't start it at this time, which like I could before, because there was 2 instructions running. I had to wait until the first one finished, and I could start scheduling DH. And then CG kicks in right after. But the add units were separate from the multiplying units. So I can start the add, okay, actually, that's what's going on. Okay, so there's like 2 things going on here that are weird. So first of all, there's R's before the S's. Can someone tell me why?
Because you can start it, but you don't have the slot to start it.
Not quite. So it's more about how we related running to start. There's nothing to say that I can't set the running variable to 1 before it starts. The running was only kind of there so I could capture the dependence across time. So the solver, seeing that it doesn't matter if I put the running time at that time on or not, it just did it. So what I can do is add a small penalty to the objective that say, hey, if you can, make the running variable go to 0. But I put a very small number in front of it, so it's not going to change the solution. It's just going to get those things down to 0. I could come up with additional constraints that'll enforce them to be 0, but this is just as good and doesn't increase the problem size anymore. So if I solve it again, now it's cleaned up. I like the ones that were floating out in the middle of the ether over there, but ghosts in the shell, I guess. So OK, now we've got it. So here's something that I find pretty interesting. So we start the two multipliers at time 1 and time 2. So at the end of time 4, they're done. And I could start the addition. It does not start that addition. In fact, it waits quite a while before starting it. Now, the reason is it could have started it earlier, but it would not have helped it. Because the limiting factor is that I can only start these multipliers so quickly. The very first time the multipliers could possibly be done is how it's scheduled right now. So given that's the first time the multipliers could start, that's the first possible time that this addition could start. And so the first possible time the last addition could start is this. This addition, essentially, is not on the binding path. It's not on the critical path. And if you're a project management person, the critical path is all you think about. So basically, because ABEF is not on the critical path, there's multiple possible places we could have started. In fact, I think there's 3 times we could have started it. It picked the last possible time. Now, we could add an incentive to start every operation as soon as possible, or not. And I have a feeling that once we add constraints for register allocation, it would not do this. I might be constrained into picking something more strategic for each one. Now, we're kind of going over time. So I want to, in this notebook, I extend this to a matrix vector product of a 4x4 matrix times a vector, which is just 4 dot products. But the interesting thing about that is that now you can start the second dot product before the first dot product's even finished. So I have the same setup, but we're kind of interleaving the dot products. So we're not running them sequentially. And the solution is pretty satisfying. But if we do the full 4x4 matrix vector product, CBC does not really handle it. At least didn't handle it in the time I was willing to wait. So if I run it, however, with the Garobi commercial solver, the code's pretty cool, I think. I made a little operation type, and I made a little tree and everything. You should check it out. I'm pretty proud. So that's going to solve, and it's going to take about 60 seconds to solve. So it gets chunky. And this is probably why compilers do not use exact methods, because it wouldn't scale. But if we had a really, really, really important thing, like an open blast kernel, just saying. So that's chewing away. So we can come back to that once it's cooked, my laptop. And in the remaining 10 minutes, which is I'm probably just going to blow past by 5, I wanted to present this rocketry control problem. So this is kind of fun. This guy is Robert Goddard, American rocket pioneer. He basically made liquid-fueled rockets a thing. And being an engineer, his goal was to make things go big and fast and high. And then the question is, if I have a liquid-fueled rocket, how do I achieve these goals of big and fast and high? In particular, high. And so what we're going to look at is this problem that I've seen called the Goddard rocket control problem. And very simply, we have a rocket. I'm just going to go pretty quickly through the setup. We have a rocket. It's just going to go straight up. There's no, it's not two-dimensional, it's just a one-dimensional problem. We have a rocket, it's going straight up. So the rocket has 2 states at each point in time. And has a velocity and an altitude. Okay? The other thing it has is mass, which it's losing quite quickly, perhaps. So it has a certain initial mass, which is the rocket and its fuel. And at the end of its burn, it'll just have the mass of the rocket itself. So we have the mass of the rocket and the fuel that's left at each time t. And we'll start at an altitude of h0, a velocity of 0, and a mass of m0. And mc will be the fraction of the mass that is the rocket itself. So obviously we can't go less than mc0 because then we're, I don't know, burning the rocket booster itself, which is probably it's been known to cause issues if you use your own infrastructure as fuel, from what I hear. Eject the warp core and such. So the control we have, we're going to assume we have complete control of thrust. So for a liquid rocket motor, this is probably not the craziest thing, but I doubt we have such fine-grained control in any real system. But we're going to pretend we can completely control the thrust and fling it around whatever we want. But we have a limit on how high the thrust can go. The thrust is going to be measured in, it's like I think it's like force, like newtons. But we're going to make everything dimensionless, so I'm not going to dwell on the units. So we control the thrust, and then we have our dynamics. So the rocket is affected by gravity, and the gravity will decrease as we go higher. So that's what this little function is saying. And then most excitingly, we have lovely nonlinear drag. So the drag function is a function of height and velocity. So v squared is going to be the velocity squared. dc is your drag coefficient. And then we have a term to basically capture air density as we go higher. It's getting thinner and thinner. So if you haven't guessed already, nonlinear optimization is happening. Really nonlinear optimization is happening. We've got squareds, we've got exponents of variables, and whoa, boy, we're in a long way from where we just were. Everything's continuous. And then let's link it all together. So this is just some kinematic motions of equations. We're not getting relativistic here. The rate of ascent is equal to the velocity. Okay. Acceleration is thrust minus drag, normalized by the mass remaining, F equals ma kind of stuff, and gravity. And the rate of mass loss is the thrust divided by the impulse of the fuel. So the higher the thrust goes, the more quickly we're going to burn the fuel. And that's all we've got. So the optimization problem is to maximize the altitude of the rocket, And we're going to, I'm not going to say in a certain time window or anything else. I'm just going to maximize the altitude of a rocket. And as part of the optimization problem, we'll be optimizing over the time window that takes place in. That's actually part of the problem itself. To turn all these differential equations into something we can model, we're going to discretize time. So we're going to split time into n chunks of equal width. And the width of that time step is delta t. And that's part of the optimization problem, is to pick delta t. And thus, I can say just maximize altitude at the last time step. So it can pick the time step size itself so that the simulation basically ends at that time. So we've discretized time. Now we need to discretize our differential equations. So if you are familiar with the rectangular rule of approximating a function just by kind of integrating it by taking rectangular chunks, we could do that. I'm going to take it one step further and make it a trapezoidal rule. Has anyone ever seen that paper from the late 90s in a health journal where they reinvent the trapezoidal rule and it has like 100 citations? It's scary over there. But this is what, so we're going to use the trapezoidal rule to turn our continuous differential equations into this sort of discretized version, numerical integration. So it's easy to see what we're doing for this one. The function, say, mass at time t plus delta t minus the function at time t is equivalent to delta t times, wow, I don't know why it says v, f dash, the gradient, delta t times the gradient. So we're just doing a simple translation of these differential equations into a discretized form. And what these things are constraints on our decision variables. So what we really want to optimize, what we really want to understand is thrust, but at the same time, we're going to have to decide. We're going to have to optimize over the mass profile, the velocity profile, and the altitude profile, but they're all linked by these constraints. The data is not mine, and it's all being put into dimensionless units. The only thing that's really understandable is MC, which is the mass fraction that is the rocket. So it's 40% fuel, 60% rocket, which probably is completely unrealistic. But that's what it is. So the initial solution is pretty interesting because when things get really nonlinear, this is pretty much just all the guarantees go out the window. And what we're going to do to address that is we're going to start from a solution that's somewhat reasonable. So, I mean, height is 1 at all times. That doesn't seem sensible. I don't know. I took it from a paper, so maybe that's wrong. But we're going to set velocity and mass to kind of be smooth linear functions across time. So the mass is going to linearly ramp down to its minimum. The velocity is going to ramp up, and we're going to fix the initial time horizon length to 1, and thus the step size to 1 over n. And without further ado, let's build the model real quickly. So we're going to load, jump, and IPOpt, which is a nonlinear friendly solver. The only other solver that we would have that could really tackle this problem is nitro.jl, which nitro is a commercial solver. So you have to pay for that. Let's load that. I'm going to set the solver to IPOpt solver. I don't actually need to. It would have just used IPOpt automatically because it's a nonlinear problem we're about to formulate. But you might want to pass print level equals 0 in to suppress the output. So this cell is just the data. I'm going to use 800 time steps, which is probably the most interesting thing in there. Let's set up our model then. So we're going to create a variable, delta t. It's non-negative. See that little LaTeX in there? Yeah, we got LaTeX. So delta t is greater than or equal to 0, and the starting value, the starting guess, is going to be 1 over n. And then I'm going to create a nonlinear expression. So in nonlinear optimization especially, we find that we have these little common sub-expressions we want to sprinkle throughout the problem. And so the first one of these I'm going to make of many is to define a nonlinear expression tf, which is equal to delta t plus n. That's the final time. So I'm going to make some more interesting ones than that in a moment. So our state variables, velocity was non-negative, and we're going to index it from time step 0 to n. So we actually have n plus 1 times? I don't know. Let's not think about that right now. Height is greater than or equal to h0, and mass is between the final mass, which is just the rocket itself, and the initial mass. Okay. Single letter variable names everywhere because math. Control, thrust, between 0 and t max, straightforward enough. Notice I didn't provide the starting values as arguments here. I could have, but I chose to do it this way to show you an alternative way. So I explicitly call set value on the variable to set an initial value. This works for integer programming as well, where you can set an initial guess of the variables. It's a general jump thing. And it'll be used differently depending on the nature of the solver, but So that's what that's about. The objective, very simple, maximize the height at the last time step, enforce some initial conditions, and then the forces. So the trapezoidal rule has the function evaluated twice, and so it would get very messy if we had the derivative evaluated twice, so it would get very messy if we had to copy-paste all that code. So what I'm going to do is going to define a nonlinear index expression drag, indexed by time step, and this is just the drag function written out. It's a nonlinear expression, so the NL. You have to, if you're doing nonlinear stuff, you have to say, otherwise we'll assume you didn't want to do nonlinear and you've made a mistake. And we use different machinery in the back end as well, so it's kind of for us as well. But it kind of makes it explicit that what you're doing is nonlinear, because it really is a different world. I also defined a one for gravity as well. So what these nonlinear expressions let me do is write, so this is the trapezoidal integration for height. So height is height at j minus 1 plus 0.5 times delta t plus this velocity sum. But more interestingly, I think, is the acceleration, which was this kind of complex thing. And so since I've defined this nonlinear expression up here, drag j, I can kind of just drop it in. And it makes it relatively clean to write out. So you can imagine how this would look if I had to actually write out this whole expression and dump it in there. It would just be 5 lines long, and I wouldn't, well, that's how it used to be in an earlier version of Jump, and I struggled finding typos.
One thing you're doing out here is you're taking a lower dimensional problem with time and making it into a much
So the original problem, I guess, is in continuous time, which would be...
But the dimensionality is relatively low. You got velocity, you got mass.
Yep. Yeah, it's 4 dimensions, right? But each of those functions is of an arbitrary functional form, which is a much harder nonlinear optimization problem to solve.
Right, but now it's a 40-dimensional problem if you have 10 times that.
Correct. Yeah. So there we go. I'm just going to run that cell. That was nice and quick. And now, I guess Gadfly's coming up. So I'm going to solve. It's taking a little bit of time this first time because it's doing some compilation of jump, but not too long. I'll run it again just for good measure. So, and then we solve it. So I just want to point out, so this is the trace from IPOpt solving the problem. And at the end, we see it exited with an optimal solution. But this is a really cool thing. So this is the total time. This is how IPOpt reports the time. So it took, what is that, like 0.6 seconds to solve. Of that time, 0.25 seconds was solved just inside IPOpt. So IPOpt is basically doing linear algebra with the derivatives. So that's how long IPOpt took. The NLP function evaluation time is Julia's time. That's Jump's time to calculate the derivatives, which is 0.3. Now, the linear algebra time is something that we can't control, and the CPU time is something we can. And Jump has got, and that metric does very well in terms of its function. Jump and Julia can calculate these derivatives very quickly. And there are other tools out there that do nonlinear modeling and do not provide those derivatives quite as quickly. In fact, can provide them several magnitudes slower. So that's our little plug for the kind of hard work that Miles has put into, especially into making this nonlinear optimization work. So while Gadfly, that was scary quick. Maybe I already had it loaded. Oh, I probably did. Yeah, Ian, you genius. Anyway, while it's drawing, which still will take time. So back here in the other notebook, we see that the 4x4 matrix vector took some time to solve. It took 48 seconds. And you can see what I was saying here before about the gap and what optimality means. So this incumbent is the best integer solution it's found. 14 here is the best linear relaxation, where things can be 0.5, 0.3, or whatever. And what it's doing is it's doing this enumeration-like smart enumeration procedure. And it's trying to drop both this down and this up. So it found a better solution, 38, 37, 36, 34. And the lower bound gets tighter and tighter. It's coming up from 25, 26, 32. And then it finishes when the lower bound, in this case, is actually equal to floating point tolerance with the upper bound. That isn't always the case. In this case, it actually is confident it's actually found a provable optimal solution. And if we display it, you can see it's pretty damn sweet. So this operation is the last operation for the first dot product. And you can see that the second dot product starts before we're even halfway through the first dot product. And so the length it takes to do one dot product is, this is very hacky, but it's like 14 or 15 time units or something like that to finish. But the overall operation runs in, let's see, 36. So we are just over, I don't know, like 2.5 times the length of one dot product to do 4 dot products with pipelining. So we could have spent 60 time units to do each dot product sequentially, but the CPU, by exploiting its sort of low-level parallelism, is doing it 2.5 times quicker. So that's like the promise. And back here, we can see the optimal solution to our rocket control problem. Let me zoom out one more. Whoa, don't go back. So in the top left plot, this is just Gadfly using HStack and VStack, which I think is maybe not super obvious in Gadfly. If you haven't gone looking for it, you won't find it necessarily. But HStack and VStack let you plot plots together. So I've made like a little quadrature here of things. So the altitude is kind of sigmoidal. Notice that it finishes right when you think it's about to start going down, because that's what we'd optimized for. So it's kind of a curve. Mass is pretty linearly decreasing. There is a kink here. We'll get to that kink in a moment. So it burns out. The time horizon is 0.2 seconds, but it's burnt out by 0.07. And the rest of the time, it's just coasting. There's no more thrust being put in. It's just coasting through thinner and thinner air, though. Velocity ramps up pretty quick, goes through some sort of step change, hits the peak when it burns out, and then it slows down as it goes through the air and gravity takes its toll. This is probably not linear, though, I'm guessing. And then the simulation stops. It picked the time horizon to stop when it hits velocity 0, which is the same thing as saying it picked it at maximum altitude. And then finally, thrust, what we really care about. The optimal control policy is to do a maximum burn for about 0.03 seconds, cut the thrust down to about 2/3 of that, then slowly ramp it back up, and then you're out of fuel. And that's why you do nonlinear optimization, because that's not obvious. So that is the Goddard rocket control problem. And those are two very different uses of jump, one for integer programming. Everything was 0, 1, and linear. This, everything was continuous, and I don't even want to think about the derivatives. And the great thing is I didn't have to, because jump was automatically in the background there. It was compiling a function to calculate the second-order derivatives of those constraints in that objective. In fact, the combination of all of them, because what the solver wants is a relaxation of the constraints and objective all as one function. So it's like a sum of matrices with those matrices over derivatives, and it's sparse, and Miles did it all. And give Miles a pat on the back, because it's crazy awesome. So that's jump, and that's what jump can do for you if you ever want to fly to Mars. Elon Musk, you're out there on the camera. I see you. Come on. All right, and I'm done. That's everything. Anything else to? Oh, so we have JuliaOpt stickers, and if you haven't got one yet, please come down and get one, because we want to put our brand on your personal products, and you should feel lucky. Of course, it's all open source, though, right, guys? That's good. Yeah, so, and that's it. Thank you. Now, if there's any questions, feel free to ask, but you can now go, and I won't feel offended. Yes?
So I'm familiar with convex and jump.
Yes.
They both work.
Yes, they do. Hopefully.
So my question is that if I have a convex problem,
Yeah.
which one is better?
So if it's size is important. So jump is designed, because jump doesn't do complex transformations, jump can scale up to very large problems. If you're in those 10 million variable problem range, and you have any complex like indexing going on, definitely jump. If you have more than 3 indices, or your indices aren't from 1 to n, jump. If your problem is convex, but it's not super obvious and how to transform it to a problem that jump can handle, so jump doesn't have second-order cone support yet. So if your problem is much more easily representable in second-order cone form with norms and logs and debts and whatnot, convex. But if the time to generate the model is not the binding part and actually solving it is, then it might not matter so much. It's just a matter of personal preference. So if you're non-convex and you're going to have to use jump as well, because, yeah. So jump is really aimed, jump is motivated by where we came from initially, which is operations research. We have complicated indexing structures, and like the constraints are very kind of messy, and indices can be kind of messy. And so that's what we really optimized for. And convex is coming from a kind of more engineering kind of world, where a lot of it's sort of model estimation in various forms and control, which are usually more kind of blocky and have less fiddly indexing, but can have quite messy functions of those blocks. So in the talk yesterday, I had log det of a matrix, and that matrix is positive, semi-definite, and such. You know, that's not what jump's about, but convex is all over that, because that's kind of it's an engineering problem that they kind of really shine at. So it's a mixed story. Hopefully both are pretty easy to move between. They both have relatively similar kind of surface appearances. What about them? Oh, and they use the same solvers as well. So yeah, and they all use the same code. So as we add more solvers, both benefit and vice versa. So yeah. Yes?
With the instruction scheduling problem, instead of making a couple of two-dimensional arrays of binary variables, would it have been theoretically possible to just have like 7 variables that range from 1 to 20, and it would have been awkward, or is it just a non-starter with phrasing it that way?
It technically has to be possible, I guess, maybe. I think it's probably possible, but I think it would actually be surprisingly hard to model as a set of linear constraints. You have to linearize it. And the thing is with zeros, and not because you have to in some like math sense, but because to model it and solve it with these solvers, that's what they operate. They do work on general integers, but I don't know what the constraints would look like. And it's so much easier, for me at least, to think about things in a 0, 1. And the solvers are definitely very good at handling 0, 1 problems.
Solvers much prefer binary.
Yeah.
I figured this was better. I just didn't know the other one was like even possible.
Yeah. Sometimes it's so. I once tried to think through. So Sudoku, you can model as 729 binary variables, but you're tempted to think I could do 81 integer variables, and trying to write down the constraints for even that a single digit appears only once in a row, it's a mess. Whereas it's just one constraint. Well, 9 constraints for the binaries. Yeah. So it's a thought experiment I have a lot. Yeah. Was it? Yes.
How easy is it to access from jump the internals of the solvers, say basis matrices of linear programs or the various heuristic controls?
So it is easy. So what you basically do is you get the internal math prog base. You can dig through to get the math prog base abstraction. You can dig even deeper to get the actual raw C wrappers representation of the model, depending on what you need. So to get the basis, we don't expose that in jump, but it is exposed at the math prog base level. So it's at least still somewhat abstracted over any one solver. Assuming the solver supports it, of course. So CLP, we can get the basis, right? And Gurobi as well. And yep. Now, for customizing an integer programming solve, jump actually has solver-independent MIP callbacks. So you can provide a heuristic callback to generate heuristic solutions, like constraints to cut off fractional solutions, cuts in that sense, but also lazy constraints that can cut off integer solutions. So you can actually solve, for example, traveling salesman problem by lazily generating the subtor elimination constraints. So, and if we haven't abstracted over a callback, which is the case, I believe, for Cplex, we don't support the branching. So Cplex supports branching callbacks, but Gurobi doesn't, and none of the other solvers we have do. So we haven't provided an abstraction over that yet. But you can always very easily go down one level and provide it to Cplex yourself. It isn't like a first-class citizen of jump yet, but that's not because of some technical problem. It's more of a interface problem. Yeah.
Anything that your library exposes, you can get to pretty easily.
Yes.
Can you say something about the magic that's happening in the macro calls?
So you can basically imagine for a linear program as each row of the matrix being a sparse vector that we're storing as 2 vectors. One is basically indices, and the other one is values. So when you do the sum, possibly of arbitrary indexing and conditions, it's trying to pre-allocate a vector that'll be the size of that sparse row, the number of non-zeros in that row. And then it's essentially just pushing the values onto that pre-sized vector, which of course is cheap because it's pre-sized. That's essentially what it's doing for linear and quadratic problems. It's essentially just trying to very efficiently create sparse rows. And then when you hit solve, the solvers want it in like a sparse column-wise format, but that basically just means we have to just transpose it, which is a relatively cheap thing in the scheme of things. So we do not use operator overloading. If we allow it, but we don't. The macros are a way to get around operator overloading, which would require you saying like variable 1 plus variable 2 is variable 1 plus variable 2. Then you stick another variable on, and you have to generate a new object for the expression of x1 plus x2 plus x3, and so on, which generates a lot of garbage and is slow. So we avoid that, which lets you do some quite complicated indexing and sums and quite quickly. So we've scaled, in our papers about jump, we scale it up to like the tens of millions of variables range to basically stress test that thing. But you can actually make the we do support the operator overloads, but they're kind of only when you're doing really fiddly things that you can't otherwise represent with jump directly with the macros. Yeah. Yes?
So, is it possible that you can provide some simple mathematical specification, and you have another tool to automatically generate jump or convex?
Aha, my friend, you're thinking along the exact lines that I am. So we have some extensions to jump, for example. So I have an extension that I made to jump for robust optimization, which is kind of like an abstract problem, which then essentially gets turned into a jump model, and then the jump model is solved. So that's like not too far of an extension, but you could really go crazy with this and make a package that basically you could define a logistics system with facilities, customers, whatever, and then that's like the user experience, and then that package internally is generating a jump model. And unfortunately, in my opinion, there hasn't been a package yet that is along those lines, but I actually have a feeling there is user code out there that is not a registered package that is doing this. But it's something I would love to see. So there are packages using jump. So compose uses jump. Compose.jl uses jump to arrange labels. And my own package, graphLayout.jl, uses jump internally to formulate a problem to dynamically generates an internal optimization problem to arrange elements in a tree visualization. So the user doesn't see jump, but jump is being used to internally formulate a model based on user data to make the tree. So the idea is we really would love to see more and more applications of optimization being used to make packages smarter. So in fact, Tim Holy made one of the first linear programming modeling packages in Julia very, very early on because he wanted to use linear programming for optimization of layouts of windows, putting things in a form. So Cassowary is a library that's used to do that and other things. And I think OS X has it for apps. So use a kind of linear programming-like thing. So yeah, optimization as a hidden, very exciting, I think. Yeah. All right, let's have some lunch. Get out of here, guys. Come on.